Welcome to the CFPS Certification Preparation course, where we establish the foundation for your expertise in fire protection standards. This course is an unofficial, independently produced study guide and is not affiliated with, endorsed by, or connected to the National Fire Protection Association, NFPA, or the Certified Fire Protection Specialist, CFPS, certification program. All trademarks belong to their respective owners. In this opening module, we will explore the core philosophy and structural requirements of the Certified Fire Protection Specialist credential. This curriculum is designed to guide you through the complexities of fire dynamics, life safety systems, and rigorous regulatory frameworks. By mastering these principles, you position yourself as a highly qualified professional, capable of complex risk management and hazard mitigation. Achieving this certification demonstrates a profound commitment to the safety of life and property through applied engineering and scientific rigor. The CFPS exam is not merely a test of memorization, but a comprehensive assessment of your ability to apply NFPA standards in real-world scenarios. We will investigate the testing formats, domain weightings, and the specific cognitive load expected of candidates during the proctored examination. Navigate the Fire Protection Handbook and other essential codebooks with the speed and precision required for the testing environment. Through this program, you will develop the strategic study habits necessary to tackle the multi-dimensional challenges of engineering, physics, and compliance. Beyond the technical data, you will gain a firm understanding of the professional maintenance requirements and the ethical landscape of the field. We intend to simplify the transition from theoretical knowledge to practical application, ensuring you remain within the rigorous protocols established by the National Fire Protection Association. Certification is demanding, but by synthesizing the mechanics of fire science with modern safety engineering, you will solidify your reputation as an expert in the field. This orientation serves as the necessary bridge between your current experience and the disciplined, data-driven approach required for success. See you in the next lecture. Welcome to this exploration of the principles of fire dynamics, where we will build the foundation necessary to understand how fires initiate, grow, and consume energy within various environments. Fire dynamics acts as the bridge between theoretical chemistry and the practical application of fire protection engineering, requiring an analytical mindset to deconstruct how thermal energy transforms fuel into combustion products. At its core, the tetrahedron of fire, comprised of fuel, heat, oxygen, and the uninhibited chemical chain reaction, serves as the fundamental model for all fire scenarios we encounter as professionals. When we analyze ignition, we must distinguish between piloted ignition, where an external ignition source provides the activation energy, and auto-ignition, where the fuel reaches a temperature sufficient for self-sustained reaction without an external spark. Smoldering represents a unique surface oxidation process often characterized by lower temperatures, whereas flaming combustion involves complex gas phase reactions where reactive radicals propagate the fire at high rates. Understanding these phenomena requires us to look at the transition points, such as the flash point and fire point, which dictate the specific temperature at which a liquid fuel generates sufficient vapor to support ignition or sustained burning. We must also rigorously quantify the limitations of combustion by identifying the lower and upper flammability limits, which define the concentration range in which a fuel-air mixture can actually propagate a flame. Without these precise data points, any attempt to predict fire behavior in a real-world building scenario remains strictly speculative and scientifically unsound. The transition from a solid or liquid fuel into a combustible gas is fundamentally a process of thermal decomposition known as pyrolysis or simple vaporization. In this gas phase, we observe reaction mechanisms dominated by radical chain branching, where intermediary species collide and rearrange to release significant heat, further accelerating the fuel decomposition process. This feedback loop is essential to grasp, as it helps explain why fires grow at varying rates until they eventually reach a state constrained either by the amount of available fuel or the availability of oxygen. When we evaluate fuel loads, we are essentially calculating the total potential energy density that a space presents. This metric allows us to model transient fire growth profiles using established T-squared fire curves. These curves provide an idealized but highly useful mathematical representation of how fire intensity increases over time typically described as slow, medium, fast, or ultra-fast. By applying specific heat of combustion values alongside radiative fraction coefficients, we can predict how much energy is released into the surrounding environment and how much is transferred back to the fuel bed. These calculations are not merely academic exercises, but are the necessary inputs for determining the structural requirements and suppression system capacity needed to mitigate uncontrolled thermal events. The shift between fuel-controlled and ventilation-controlled regimes represents a critical juncture in any fire event, often dictating the success or failure of fire protection systems. A fuel-controlled fire is limited only by the amount of material available to burn, meaning that as we add surface area, we increase the rate of heat release linearly. Conversely, a ventilation-controlled fire is limited by the intake of air, common in compartmentalized structures where oxygen ingress is restricted by doors, windows, or building envelope integrity. Here, the stoichiometry of the fire becomes the dominant variable, as the chemical balance of oxygen and fuel determines the completeness of combustion and the potential for rapid change throughout the enclosure. We must also account for thermal inertia, which describes how quickly a material heats up and reacts, essentially quantifying the material's ability to store or conduct heat away from the surface of ignition. Higher thermal inertia can delay ignition, while lower values may allow a surface to reach its decomposition temperature almost instantaneously upon exposure to a heat flux. By mapping these physical properties against the heat release rate, we can gain a high degree of confidence in predicting how a space will respond under fire conditions. This quantitative framework is what ultimately allows us to move beyond intuition and into the realm of evidence-based fire protection. I look forward to discussing the chemistry and physics of fire with you next. Welcome back, and let us now decompose the fundamental principles governing the chemistry and physics of combustion events. This chapter is designed to provide you with the rigorous scientific foundation necessary to interpret complex fire dynamics, ensuring you are fully equipped to succeed on the CFPS examination. At the core of fire chemistry lies the concept of molecular bonding and the release of energy through exothermic reactions. When we speak of combustion, we are essentially describing a rapid oxidation process where fuel molecules react with oxygen to form stable products, typically accompanied by the liberation of heat and light. From a thermodynamic perspective, this involves the breaking of chemical bonds in the fuel, an endothermic step that requires activation energy, followed by the formation of stronger bonds in products like carbon dioxide and water, which releases significant energy. We must view this through the lens of oxidation states, where the fuel acts as the reductant and oxygen as the oxidant, shifting their electron configurations to reach a lower energy state. Understanding these states is not merely academic, as it dictates the heat of combustion and the subsequent rate at which a fire can grow within a compartment. If you grasp how specific molecular structures govern ignition susceptibility, you gain the ability to predict material behavior long before a fire reaches its peak intensity. The physics of containment requires a firm grasp of ideal gas behavior under significant thermal stress, particularly when evaluating enclosure fires. We frequently rely on the ideal gas law, identifying the relationship between pressure, volume, temperature, and the amount of substance in moles. As a fire progresses, the expansion of gases constrained by walls and ceilings demonstrates Charles's law, where volume remains constant, leading to a proportional increase in pressure, or Boyle's law, where pressure changes relative to volume shifts. These laws are critical when assessing the structural integrity of an enclosure or the potential for backdrafts and smoke explosion phenomena. Conservation of mass dictates that the sum of the mass of reactants must equal the mass of the products, yet in an enclosure, we must account for the accumulation of intermediates and the stratification of hot gases. By applying these physical laws, you move from observing smoke movement to quantifying the volumetric flow rates that drive fire spread across ventilation pathways. When looking at the fuels themselves, the molecular composition of synthetic polymers and cellulosic materials tells us everything about their decomposition pathways. Cellulosic fuels, composed of complex polysaccharides, decompose through predictable sequences of pyrolysis, yielding char, water vapor, and flammable volatiles. Synthetic materials, conversely, often exhibit more complex degradation modes, frequently producing higher concentrations of toxic gases and soot, due to their hydrocarbon-rich backbone chains. We must be able to anticipate the heat of vaporization and the specific heat capacity of these solids to determine how fast material will degrade under incident heat flux. Thermal conductivity plays a dual role here, dictating how deeply the heat penetrates a material's surface, thereby determining the effective thickness of the fuel contributing to the combustion process at any given moment. The formation of byproducts, particularly soot and toxic gases like carbon monoxide, represents a critical aspect of fire safety assessment. Soot, formed primarily through the agglomeration of carbon particles in fuel-rich zones, significantly influences the optical density of smoke, which fundamentally impairs visibility and egress. Carbon monoxide yield is a direct function of the equivalence ratio, where incomplete combustion dominates in oxygen-deprived environments, leading to lethal concentrations that overwhelm occupants long before thermal damage occurs. To translate these findings into actionable data, we utilize the fractional effective dose calculations, which aggregate the impact of various toxicants over time relative to their lethal exposure thresholds. Atmospheric physics governs how these aerosols disperse through a building, often influenced by thermal buoyancy and localized pressure differentials that dictate the migration patterns of smoke. When you master these principles, you are no longer just imagining a fire. You are calculating the exact physical and chemical risks present in a given environment. See you in the next lecture. Welcome to the chapter on heat transfer mechanisms, where we will rigorously analyze the physics driving fire propagation. We will quantify heat flow through conduction, convection, and radiation to understand how fires develop and spread within various environments. Understanding how energy moves from a fire source to surrounding materials is essential for any fire protection specialist. We begin our analysis with thermal conduction, governed by Fourier's law, which relates the heat transfer rate to the temperature gradient and the thermal conductivity of the material. When dealing with thick structural members, we often rely on the semi-infinite solid assumption to simplify transient heating calculations. This allows us to predict the temperature at a specific depth over time, provided we accurately define our boundary conditions, such as surface temperature or incident heat flux. Thermal diffusivity becomes the critical metric here, as it represents the rate at which heat distributes through a substance relative to its ability to store energy. By performing these calculations, we can estimate how long it takes for a structural component to reach its critical failure threshold during an exposure. Convection represents the exchange of thermal energy between a fire plume or hot gas layer and adjacent surfaces, governed primarily by Newton's law of cooling. The complexity of this mechanism depends on whether the flow is driven by buoyancy, known as natural convection, or by external air movement, which we classify as forced convection. To quantify this transfer, we rely on the convective heat transfer coefficient, which is highly sensitive to the geometry of the target surface and the flow regime defined by the Grashof and Prandtl numbers. A laminar flow will yield different results than a turbulent flow, and identifying the transition point is vital for accurate modeling. In fire science, we often use empirical correlations to determine these coefficients, as analytical solutions for complex shapes are rarely feasible. Proper evaluation of these parameters ensures that our models for surface heating and ignition delay are grounded in actual physics rather than mere intuition. Radiation is frequently the dominant heat transfer mechanism in large-scale fires because it does not require a material medium to propagate energy. The Stefan-Boltzmann law provides the foundation for our calculations by relating total emissive power to the fourth power of absolute temperature. Matters become more intricate when we account for the spectral nature of emission using the Planck distribution, particularly when evaluating how targets absorb energy based on their surface emissivity and absorptivity. We must also consider view factors or shape factors, which describe the geometric orientation between the fire source and the target, often requiring the use of configuration matrices. In environments containing gases like carbon dioxide and water vapor, we must go further to account for the participating media that both absorb and re-emit radiation. Exchanges allows us to predict the ignition of secondary fuels at a distance, which is a cornerstone of effective fire spread analysis. See you in the next lecture. Welcome to this deep dive into the fire plume dynamics that govern heat transport from a fire source toward potential suppression or detection systems. In this chapter, we establish the analytical foundation required to predict fire behavior in various environments and configurations. When we examine the behavior of fire, we must consider the buoyant plume as the primary mechanism for transporting energy from the fuel source upward. A fire plume is essentially a turbulent buoyancy-driven flow where the combustion products are accelerated upward due to the density difference between the hot gases and the cooler ambient air. As these hot gases rise, they pull in or entrain surrounding air, a process that determines both the total mass flow rate and the cooling profile of the plume. We generally categorize this anatomy into three distinct zones: the continuous flaming region near the base, the intermittent flaming region above it, and the buoyant thermal plume region. Understanding these transition points is critical because the heat release rate and the geometry of the source directly influence the plume's temperature and velocity at any given height. Classical correlations developed by researchers like Heskestad and McCaffrey provide us with a systematic way to calculate these variables. By applying these empirical equations, we can reliably estimate the centerline temperature and velocity, which serve as the inputs for nearly all subsequent thermal calculations in fire protection engineering. Beyond the vertical behavior in an open space, the plume often encounters physical boundaries such as a ceiling, which significantly alters the flow dynamics. Once the plume strikes an unconfined ceiling, the buoyant upward motion is obstructed, causing the gas to turn and spread horizontally as a ceiling jet. This ceiling jet is the mechanism that activates heat-based detectors and fire sprinkler heads mounted at or near the deck. Alpert's correlations remain the standard tool for predicting the time to actuation, as they account for the radial spread of the hot gas layer and the subsequent decay in temperature and velocity as the gas moves further from the stagnation point. We must be particularly careful to adjust our calculations when these flows are interrupted by geometric constraints like wall corners or beams, which can artificially trap heat and accelerate activation times compared to a wide open area. The physics remains consistent, but the boundary conditions require us to use reflection principles to model the flow properly. Failure to account for these constraints often leads to underpredicting the response time of detection systems. The complexity increases significantly when we introduce specialized plume configurations, such as balcony spill plumes or window plumes resulting from compartment venting. A window plume occurs when a fire inside a room vents through an opening, effectively creating a new virtual source for the smoke outside the structure. Similarly, balcony spill plumes occur when smoke flows out of a doorway and travels upward along the exterior facade, potentially re-entering the building at higher levels. These scenarios demand an understanding of virtual origin concepts, allowing us to treat non-point sources as equivalent point sources to simplify the math. Furthermore, we must address external environmental factors such as crosswinds or internal stratification. A crosswind can lean the plume, reducing the effectiveness of air entrainment and pushing the hot gases away from the intended detection zone. Stratification, where a layer of hot gas already exists beneath the ceiling, acts as a barrier that limits the buoyant rise of the plume, a condition that frequently leads to late detection or non-actuation if the design does not account for the ceiling jet's inability to penetrate the layer. See you in the next lesson. Welcome to the module on enclosure fire behavior, where we analyze the complex dynamics that transform a simple ignition into a room-wide fire. Mastering these principles will elevate your professional capability to perform rigorous fire safety evaluations that set you apart as a certified fire protection specialist. When we observe fire within an enclosure, we must step away from the simplified view of open flaming and look at the compartment as a system. The evolution of a fire in a confined space follows a distinct chronological progression, starting with the incipient phase, where the combustion is localized to the fuel source. As combustion proceeds, the plume rises and strikes the ceiling, creating an expanding hot gas layer that begins to redistribute heat back onto other combustible items in the room. This process is fundamentally a balance of mass and energy exchange, where the heat released by the burning fuel interacts with the ventilation openings to dictate the fire's growth rate. If we consider the compartment as a two-zone model, we identify an upper hot smoke layer separated from a cooler, clearer lower layer by a neutral plane. This neutral plane is the pressure boundary where atmospheric pressure equals the pressure of the hot gases, and its height is a primary indicator of smoke stratification. Maintaining control over this vertical layering is often the difference between a manageable incident and a total loss of structural integrity. The transition from a growing fire to flashover represents a critical thermal threshold that fundamentally changes the fire's behavior. Flashover occurs when the entire surface area of all combustible contents in an enclosure is simultaneously subjected to heating from the concentrated radiation of the hot gas layer. We apply the Thomas flashover correlation, the Bobrowski's method, or the MQH method to predict whether a specific set of fuel loads and ventilation conditions will result in this catastrophic event. These mathematical models rely heavily on the opening factor, which accounts for the area of windows or doors and their height, influencing the inflow of air necessary for combustion. If an enclosure lacks sufficient oxygen but has high temperatures, we risk a backdraft, where the sudden introduction of oxygen results in a violent deflagration as the fire seeks to achieve equilibrium. Engineers utilize these predictive calculations to determine the necessary fire resistance ratings for compartment walls, ensuring that the boundaries can withstand the heat flux long enough for evacuation or suppression. Once a compartment reaches flashover, the fire enters the fully developed phase where total heat release is largely dependent on the available oxygen supply. In this stage, the fire is often ventilation controlled, meaning the rate of combustion is strictly bounded by the amount of air that can enter through openings. The temperature time curve in a post-flashover environment becomes extreme, often following the standardized ISO 834 or ASTM E19 curves, which we use to test the endurance of structural members. We must also account for the exterior dynamics, specifically flame projection from windows that can extend to the facade of the building. Such projections create a secondary hazard by heating adjacent floors or buildings, potentially breaching fire-rated barriers through radiant transfer and direct flame impingement. The ability to model these exterior plume dynamics is essential when analyzing high-rise buildings where vertical fire spread represents a significant threat to life safety. By decomposing these physical processes into mass and energy balances, we move from guesswork to evidence-based fire protection engineering. See you in our next session. Welcome to the chapter on Applied Thermal Sciences, where we synthesize thermodynamics, fluid mechanics, and heat transfer to solve complex fire protection engineering challenges. In this series of lessons, we bridge the gap between theoretical physics and practical site-specific hazard assessments. You will move beyond simple fire dynamics models to perform rigorous energy balance calculations and evaluate the transient thermal responses of materials under duress. We will look at how localized fire sources interact with enclosure boundaries and how ventilation parameters dictate the growth or decay of a fire scenario. By the end of this chapter, you will be able to apply high-level computations to heat release rate profiles while accounting for experimental calorimetry and scaling laws. This is what sets a standard fire inspector apart from a certified fire protection specialist who can defend performance-based designs with scientific rigor. When we approach applied thermal sciences, we must first address the integration of disparate fluid mechanics and heat transfer principles into a cohesive unit. A fire is fundamentally a thermodynamic event that exists within a fluid environment, usually atmospheric air, inside an enclosure. To conduct a reliable hazard assessment, we must account for the mass and energy balance of the system. This requires us to look at the fire as a volumetric heat source integrated with enclosure boundaries. Thermal feedback from walls and ceilings increases the energy density within the space, which in turn accelerates the pyrolysis of surrounding fuel sources. We use Froude modeling to maintain dynamic similarity between a fire in a real-world building and a small-scale experimental study. This scaling is essential because we cannot always test materials at full scale, yet we must ensure our performance predictions are valid. The thermodynamics of suppression agents is another pillar we must master to ensure our engineering solutions provide real protection. When we deploy water, we are not simply adding mass to a fire, but utilizing the high specific heat and latent heat of vaporization to remove energy from the combustion process. As water droplets enter a fire plume, they absorb energy to reach saturation temperature and eventually undergo a phase change from liquid to vapor. This process effectively dilutes the fuel-air mixture and displaces oxygen, reducing the reaction rate significantly. In the case of inert gas systems, the mechanism of suppression shifts primarily toward physical displacement and heat capacity absorption. Understanding these microscopic interactions is the difference between specifying a system that simply satisfies a code checklist and one that provides technically validated fire mitigation. Analyzing transient thermal responses of target materials requires a shift in how we perceive heat transfer across boundaries. We are often tasked with determining how quickly a structural component or a target item will reach a critical temperature of failure. This involves a one-dimensional heat conduction equation modified for transient states, where the temperature of the material changes as a function of both depth and time. We must account for the convective heat flux from the plume or sealing jet and the radiant flux from the hot smoke layer. When we perform these energy balance calculations, we are essentially building a mathematical model of survival versus failure. If the energy input through radiation and convection exceeds the material's capacity to conduct that heat away, we observe a temperature rise that can culminate in ignition or structural degradation. Ventilation parameters add a layer of complexity that often dictates the outcome of an enclosure fire. Fresh air intake provides oxygen, but it also alters the thermodynamics of the plume by changing the fluid dynamics of the flow field. Excessive ventilation can flush the heat out of the building, potentially preventing a flashover, but it can also increase the burning rate by providing additional oxidizer. We measure the dilutive effects of ventilation by calculating the change in enthalpy flow across the boundaries of the enclosure. Mastering these principles allows you to develop site-specific performance-based design criteria that stand up to peer review. It is not enough to rely on prescriptive tables found in codes. You must understand the underlying science to adapt those requirements to non-standard fire scenarios. See you in the next lesson. Welcome to this chapter, where we will rigorously analyze the technical requirements for designing and calculating means of egress systems according to the NFPA standards. This section provides the essential knowledge required to master capacity calculations, travel distance limitations, and complex egress geometry for any professional certification. Designing a functional means of egress requires a disciplined approach to mathematical capacity and spatial geometry, as defined by the NFPA Life Safety Code. We begin by identifying the total occupant load of a space, which serves as the fundamental input for determining the necessary width of every egress component. The code dictates specific capacity factors for different occupancy types, which are expressed in inches per occupant for stairs and level components. You must treat these as absolute minimums, ensuring that the cumulative width of your exits accounts for the largest potential occupant surge rather than an average daily count. A common error involves ignoring the bottleneck effect where multiple corridors converge into a single exit access point. Therefore, you must calculate the capacity based on the most restrictive component in the path. If your egress path transitions from a wide corridor to a narrower stairwell, the stairwell governs the total flow capacity of that entire section. Travel distance is another critical parameter that forces us to reconcile building dimensions with fire safety performance. Every occupant must have a path of travel that terminates at an exit, and the length of that path is constrained by specific variables in the code. We focus on the common path of travel, the distance an occupant must traverse before they are presented with a choice of two directions, and the total travel distance to reach an exit. You will find that these limits depend heavily on whether the building is protected by automatic sprinkler systems. The inclusion of life safety sprinklers often provides a generous multiplier in permitted travel distances, effectively acknowledging the delay in fire growth and toxic smoke production. We must also carefully evaluate dead-end corridors, which are essentially traps if they exceed permitted lengths, as occupants might unknowingly travel toward a fire source with no alternative route. Geometric arrangements within the floor plan are governed by the principle of remoteness, which prevents a single incident from blocking all available means of escape. The standard rule of thumb for many occupancies is the 1/2 diagonal rule, which mandates that the distance between two exits must be no less than half the length of the maximum overall diagonal dimension of the building or area served. If a floor plan is complex or irregular, this measurement is taken along the natural path of travel, not just in a straight line through walls. This requirement ensures that as long as the exits are separated by this minimum distance, the probability of both becoming impassable simultaneously due to a localized fire is significantly reduced. You should always look for opportunities to increase this separation beyond the minimum. as maximizing the distance between exits provides an additional buffer against unforeseen structural failures or rapid flame spread. Exit discharge and the transition to the public way require just as much scrutiny as the interior paths. Many professionals forget that the means of egress does not end at the exterior door, but rather at the public way itself. If an exit discharges into a courtyard or an alley, that route must be protected and maintained to ensure it provides the same level of safety as the interior exit passageways. Egress through intervening spaces is generally discouraged, but permitted under specific, highly controlled circumstances where the nature of the hazard is low and the path is clearly marked and protected. Furthermore, we must account for non-standard equipment, such as alternating tread devices or fire escapes in existing buildings, which are restricted to specific applications where stairs are physically impossible. Each of these components must align with the total egress capacity of the floor, ensuring that the flow of people is never choked at the termination point. Mastering these calculations requires a methodical audit of every hallway, door, and stair flight in your facility model. By strictly applying the width factors, checking the geometry for remoteness, and accurately applying the impact of suppression systems, you create a robust design that satisfies the regulatory requirements for public safety. Consistent practice with these formulas ensures that you can identify compliance gaps during plan reviews. See you in the next lecture. Welcome back. We are now turning our attention to the chapter on occupant load determination, where we will master the technical requirements for establishing safe egress limits. By the end of this module, you will possess the ability to perform complex calculations required for professional safety certification. Determining the occupant load is a fundamental task in life safety, as it dictates the minimum width of exits and the total capacity of egress components. At its core, the occupant load is simply the number of persons for which the means of egress of a building or portion thereof is designed. When we approach a floor plan, the first step is to establish whether we are calculating based on the gross floor area or the net floor area. The gross floor area typically includes the entire area within the inside of the exterior walls, while the net floor area focuses on the actual occupied space, excluding corridors, restrooms, and walls. For example, in a mercantile occupancy, the code often mandates using a gross floor area factor, whereas a classroom requires a net occupant load calculation because we are concerned only with the space occupied by students at desks. You must consistently apply the specific occupant load factors found in the NFPA 101 or building codes, which are expressed as square feet per person for various occupancy types. Failure to distinguish between these two interpretations often leads to either overestimating the safety of a building or, conversely, creating a design that is unnecessarily restrictive and expensive to build. Complexities arise quickly when dealing with mixed occupancies or accessory spaces, which require a methodical, layered approach. If a single building contains multiple types of occupancies, such as an office space that shares a floor with a small merchandise area, each zone must be calculated according to its specific use. You essentially define the boundaries for each occupancy type, apply the corresponding load factor, and sum the results to determine the total occupant load for that floor. Accessory spaces, however, are treated differently because they are considered subservient to the main occupancy. If the accessory space is less than 10% of the floor area, you may sometimes be permitted to treat the entire area under the dominant occupancies factor. This nuance is critical when reviewing architectural plans, as failing to account for the primary use of a space can lead to a significant discrepancy in the calculated egress capacity. You should always look for the most restrictive regulation when multiple rules seem to apply to a single threshold. Precision here acts as a safeguard, ensuring that the infrastructure is capable of handling the population density during a fire event. When we shift our focus to assembly uses, the distinction between concentrated and less dense arrangements becomes the primary driver of your design calculations. A room with fixed seating is relatively straightforward, as you simply count the number of chairs, benches, or seats assigned to defined locations. However, when the configuration is open, such as in a dance hall or a multi-purpose room where furniture is frequently moved, you must assume the densest possible occupant load. The codes distinguish between concentrated use, typically calculated at 7 square feet per person, and less dense arrangements which may permit 15 square feet per person. These variations are not arbitrary. They reflect the reality of how human behavior and physical movement change based on the availability of personal space. Furthermore, the presence of physical barriers, such as decorative columns or fixed counters, acts as a practical constraint on how many people can realistically fit, though you should never rely on these as a justification for reduced egress unless they are permanent and fixed. As a specialist, you are responsible for documenting the basis of these decisions, ensuring that the occupant load is legally defensible and physically safe. Managing transient populations and bleacher configurations requires you to look beyond the static layout of a building at any given moment. In facilities like stadiums or event centers, the occupant load can shift dramatically, depending on the specific event, requiring you to account for the highest legally permissible threshold. Regarding bleachers, you must calculate the count based on the linear length of the seating surface divided by the required unit of measurement per person. It is often helpful to visualize the flow of people moving from these high-density areas into the main aisles and towards the exits to spot potential bottlenecks. If the anticipated occupant load exceeds the currently approved capacity, you are mandated to either reduce the ingress capability through physical intervention or increase the egress capacity through wider exits and exit paths. Any documented approval for increased occupant loads must be rigorously verified against the available egress widths specified by the applicable codes. Maintaining these thresholds is essential for ensuring that even in the most crowded scenarios, the occupants can exit the facility within a safe time frame. See you in the next lecture. Welcome back to our exploration of the Life Safety Code, where we now focus on the essential requirements for emergency lighting systems. Emergency lighting is not merely a convenience, but a fundamental life safety component designed to ensure that occupants can vacate a building during an electrical power failure. When normal lighting fails, the system must provide immediate illumination along the entire egress path, starting from any point within the building and continuing to the point of exit discharge. The core requirement mandates an initial average illumination of at least 1 foot candle along the path of travel, measured at the floor level. It is crucial to remember that this intensity is permitted to decay over the required 90-minute duration, provided it does not drop below an average of 0.6 foot candles at any point. This gradual performance degradation is a critical design metric that engineers must account for when sizing battery banks and evaluating discharge curves to ensure that the illumination remains functional throughout the life of the event. The reliability of these systems often hinges on the transition phase between normal power and the emergency source. When utilizing an emergency generator, the transfer switch must operate within a maximum latency of 10 seconds to comply with the standard requirements for life safety illumination. This short window is intentionally narrow to account for human visual adaptation physiology, as the human eye requires time to adjust to sudden shifts in light levels, particularly in the presence of smoke. Beyond the illumination levels, we must consider the uniformity ratio, which serves to prevent areas of high contrast that could lead to disorientation or visual distress during an evacuation. A well-designed system avoids shadows and glare, as these can obscure the very hazards or navigational markers that occupants need to observe during a fire event. In modern complex environments, the integration of emergency lighting with intelligent building management systems offers significant advantages for ongoing monitoring and diagnostic performance. These systems can provide automated testing protocols, which are required periodically to ensure that battery modules, lamps, and inverters are operational without requiring manual intervention for every inspection. However, even with advanced automation, physical placement remains a matter of sound fundamental design. You must ensure that luminaires are strategically positioned to illuminate stair treads, landings, and obstacles that might pose a trip hazard. If you are relying on photoluminescent materials for pathway marking, they must be periodically charged by a high-intensity light source to function effectively, and this requirement must be integrated into the maintenance schedule of the facility as a whole. Smoke obscuration presents a significant challenge to traditional ceiling-mounted emergency lighting, as smoke layers naturally descend from the top of an enclosure. In spaces where smoke accumulation is likely, floor proximity pathway markings or intermediate-level lighting systems become necessary to maintain visibility when the upper atmosphere is obscured. These systems utilize low-mounted LED arrays or high-performance photoluminescent strips to guide occupants when visibility distance at eye level is reduced below functional thresholds. The challenge here is to ensure that the light output from these devices does not create intense glare that blinds occupants while they're crawling or moving in low visibility conditions. Effective engineering requires a balanced approach where the signal-to-noise ratio of the visual guidance system is kept high enough to be seen through light to medium smoke density without causing physiological discomfort. When considering the infrastructure supporting these lights, keep in mind the difference between self-contained battery units and central battery or generator-fed systems. Self-contained units offer decentralized reliability, meaning a single component failure only affects a localized area, whereas a central system requires a hardened electrical distribution path that must be protected from fire damage for the duration of the emergency. If you are designing for a high occupancy hazard, the selection of the power source is often driven by the physical architecture of the building and the expected fire load. Regardless of the chosen technology, the primary goal remains absolute navigational clarity during a catastrophic power failure, which requires meticulous attention to both the hardware specifications and the environmental context into which they are installed. See you in the next lecture. Welcome to this chapter, where we will examine the rigorous requirements for exit signage and wayfinding systems in life safety design. We will dissect the technical standards for illumination, placement, and visual legibility that ensure occupants can navigate to safety during a fire event. Effective exit signage is not merely a matter of convenience, but a fundamental component of the egress system that dictates occupant behavior under duress. When we discuss exit signs, we are essentially talking about the visual communication layer that translates architectural space into a navigable path. The primary goal is to provide a clear, unambiguous signal to the nearest exit in a smoke-obscured or low-lighting environment. Codes like NFPA 101 prioritize visibility, requiring that signs be positioned so they are visible from any point of the exit access path. This implies that if an occupant is standing anywhere within a corridor, they should be able to identify the direction towards safety without hesitation. If a clear line of sight to an exit is obstructed, directional indicators must be provided to guide the flow of movement. This is particularly relevant in complex environments with long hallways or sprawling facilities where exits may not be immediately intuitive. The physical characteristics of these signs are governed by strict engineering standards to ensure they function when it matters most. Lettering size, width, and contrast are not arbitrary choices, but calculated dimensions meant to maximize recognition. Typically, we require the letters to be at least 6 inches high, with a stroke width of at least 3/4 of an inch. Contrast is equally important. A red or green legend on a contrasting background, usually white, must be maintained to ensure the characters remain discernible even at a distance. When we talk about illumination, we generally categorize them as internally or externally illuminated, or sometimes photoluminescent. Internally illuminated signs are often preferred because they contain their own light source, providing a consistent visual anchor. Photoluminescent signs, while useful, rely on a charging period from ambient light, which necessitates careful consideration of the lighting environment they occupy. Power reliability is a significant design constraint that requires deep consideration of the electrical architecture. Exit signs cannot merely rely on the general building power because a fire event often involves utility failure or circuit breakers tripping. Therefore, these systems must be connected to dedicated branch circuits that are not susceptible to being switched off by unauthorized personnel. Beyond the main power, there is a mandated requirement for emergency power, typically provided by battery backups that sustain the sign for a minimum of 90 minutes. These batteries are subject to rigorous maintenance and testing protocols to ensure they do not fail the moment they are needed. We often overlook the structural aspects of these signs, but they must be securely fastened to prevent them from becoming hazards during seismic events or mechanical failures within the ceiling assembly. In institutional or complex architectural settings, we occasionally require supplementary signage to avoid confusion for the occupants. This includes tactile signage for the visually impaired and specific floor designation markers within enclosed stairwells. A floor designation sign helps someone realize exactly where they are in the building, which provides critical information to responding fire department personnel. Conversely, we must also consider the placement of no exit signs on doors that might be mistaken for an exit during a panic situation. If a door leads to a basement, a closet, or an area that does not provide a safe route outside, code often mandates labeling it to prevent a dead-end mistake. These small, granular details are exactly what distinguishes a compliant egress design from a dangerous one, as the psychological aspect of panic often leads people to follow familiar architectural clues rather than logic. When analyzing these installations, remember that visibility and authority are the two pillars of effective wayfinding. If you are designing for a theater or a high-rise, the density of the occupant load will likely necessitate higher intensity illumination or multiple signs per location. Always verify that your chosen signage meets the specific luminous intensity requirements set forth in the current edition of the code. Maintain a strict adherence to these technical specifications, as they represent the minimum threshold for performance. As engineers or safety specialists, we are creating a reliable system that bridges the gap between the built environment and the safety of the individual human life. The codes provide these rigid specifications to eliminate guesswork and to standardize the wayfinding experience across all building sectors. See you in the next lecture. Welcome back. This chapter focuses on the complex interplay between human psychology, physiological limitations, and decision-making processes during fire emergencies to help you master the behavioral aspects of life safety. In this chapter, we will dissect the behavioral sequence model that governs how occupants react to fire events, moving from initial perception to the final act of evacuation. Understanding that human behavior is not chaotic, but rather a structured sequence of perception, interpretation, decision, and action is vital for anyone designing safe egress systems. We will move past the popular misconception of blind mass panic, which research consistently shows to be rare and socially disorganized, and instead focus on rational self-preservation strategies. You will learn how individuals spend significant time in pre-movement activities, often attempting to finish tasks or seeking information before committing to evacuation. By analyzing these phases, we can better predict how occupants will behave when faced with environmental changes, such as the appearance of smoke or the sound of an alarm. We will also examine the cognitive dissonance that often occurs when a person is faced with conflicting information, such as an alarm ringing despite a lack of visible smoke. Effectively managing these factors requires a blend of sociological insight and rigorous engineering logic to ensure that your fire protection designs account for the realities of human psychology. The behavioral sequence model starts when a person perceives a cue, such as the smell of smoke or the activation of an audible fire alarm system. This perception phase is immediately followed by interpretation, where the individual determines the meaning of the cue and assesses the potential threat level. It is during this interpretive phase that we often observe milling behavior, which is a process where individuals look to others to confirm that an emergency is actually occurring. This social validation process is a central component of human decision-making and acts as a filter that can delay the movement phase. Once an individual decides that there is a credible threat, they must move through the decision process to select a course of action from a limited set of personal options. This selection is highly influenced by the individual's familiarity with the building and their previous experiences with evacuation drills. Action, the final phase, involves physical movement toward an exit or a place of refuge. And it is here where the gap between theory and actual performance often widens. We must account for the reality that people do not typically act as individual machines, but rather exist as members of a social network that dictates their speed and direction. Leader-follower dynamics play a massive role in how people behave during an emergency, often overriding individual logic in favor of group cohesion. Studies consistently show that in the initial stages of a discovery, people lean on those around them to decide whether to continue their current activity or start moving toward an alarm. This is particularly relevant in crowded environments like high-rise offices or retail centers where high occupant density makes individual decision-making secondary to group movement. We must also consider the significant physical limitations that influence the total evacuation timeline, specifically for those with mobility, sensory, or cognitive impairments. For instance, an individual with a mobility impairment will have a significantly higher pre-movement time due to the cognitive task of navigating an unfamiliar path or waiting for assistance. When we design egress paths, we must assume that the population is diverse and that the slowest common denominator defines the safety limit for the entire group. The integration of these demographic and sociological realities into our egress modeling allows for results that are actually applicable in a real-world disaster scenario. Physiologically, we must balance these behavioral observations with the actual chemical thresholds that cause human incapacitation. We use fractional effective dose or FED calculations to estimate the impact of toxic smoke inhalation, focusing primarily on carbon monoxide, hydrogen cyanide, and thermal irritation. Carbon monoxide acts as a chemical asphyxiant by hindering the blood's ability to carry oxygen, while hydrogen cyanide interferes with cellular respiration, rapidly decreasing a person's cognitive ability to make decisions. The FED is essentially a predictive tool that allows us to quantify how much of a toxic dose an individual has received over a specific time, given their specific respiration rate. As an occupant moves through a smoke-logged corridor, their physical exertion increases their breathing rate, which in turn accelerates the intake of toxic gases and reduces their chance of successful egress. If the environment produces enough toxicity to reach a critical FED, the occupant will likely become incapacitated before they can navigate past the hazard. Designing for safety requires us to ensure that the time taken to exit the space is significantly shorter than the time required for the accumulation of a lethal dose of these toxicants. See you in the next lecture. Welcome back. In this chapter, we will examine how egress requirements shift when we move from general occupancy classifications to specialized building types that defy standard exit design. When we discuss egress, we often fall into the trap of thinking about a generic office floor plate with a fixed occupant load. However, the NFPA 101 code standards evolve significantly when the building function limits the mobility or the cognitive capacity of the occupants. In healthcare facilities, the fundamental concept shifts from total evacuation to a defend-in-place strategy. This approach relies on smoke compartments that act as physical fire barriers, allowing staff to move patients horizontally into an adjacent, safe area. Horizontal exits are not merely doors and walls. They are engineered solutions that must maintain a specific fire resistance rating while allowing the rapid movement of beds and specialized medical equipment. We must evaluate these zones based on the total time required for a controlled relocation, which is a calculation far more complex than simple travel distance metrics. The reliance on staff intervention assumes that the personnel are trained, present, and capable of executing an emergency plan under extreme physical and psychological stress. High-rise structures present an entirely different set of technical challenges due to the sheer vertical distance and the potential for extended evacuation times. We cannot rely on the traditional exit transition to the street level for every occupant, because the time required would far exceed the available safe egress time. Instead, we see the implementation of phased evacuation, where floors in immediate proximity to the fire participate in the clearing process while others safely shelter until directed otherwise. This strategy necessitates sophisticated fire alarm and communication systems that can provide clear, localized instructions. Furthermore, the use of elevators for occupant egress is no longer a purely theoretical debate. It is an integrated engineering reality that requires rigorous redundancy in power supplies, water protection for shafts, and lobby pressurization to ensure those shafts remain tenable for the duration of the event. Assembly occupancies, such as stadiums or concert venues, introduce the problematic variable of crowd dynamics, where human behavior and density reach critical thresholds. Unlike standard commercial spaces, these venues must accommodate massive, sudden egress demands where the primary exit width is not just a calculation, but an absolute structural limit. We have to look closely at the main entrance requirements, which often need to account for more than half of the total egress capacity due to the familiarity of the exit path for the users. Crowd crush is not an abstract concept, but a quantifiable physical force that designers must mitigate through careful aisle width management and the reduction of convergence points. If the flow of bodies exceeds the discharge capacity of the exits, the resulting bottleneck transforms a managed exit process into a life-threatening, stationary obstacle. We also confront the binary conflict between security and safety in detention and correctional facilities, where lock and key protocols are inherently opposed to the free egress requirements of the code. In these environments, we utilize controlled movement strategies where staff can remotely unlock specific doors in sequence to guide occupants to secure zones. Moving into hazardous industrial environments, we require high-speed abort mechanisms and emergency egress pathways that are shielded from the specific threat, such as chemical spills or deflagration zones. Similarly, underground structures and windowless buildings force us to rely entirely on mechanical ventilation and robust fire protection systems, as natural venting is non-existent. These specialized designs demonstrate that egress is never a one-size-fits-all solution, but rather an outcome of the operational intent and the inherent risks of the structure itself. See you in the next lecture. Welcome back. In this chapter, we will master water supply hydraulics, a critical pillar of fire protection engineering that separates successful designs from catastrophic failures. Water supply hydraulics is the fundamental discipline that ensures your fire protection systems perform as intended during an emergency. We will move beyond simple rules of thumb and dive deep into the rigorous fluid dynamics required to evaluate municipal water delivery capabilities and complex piping networks. By mastering these calculations, you will gain the competence to verify if a water source can reliably support the high demand of modern automatic suppression systems. This module is essential for passing the CFPS exam and proving your ability to protect life and property with engineering precision. To understand water supply, we begin with hydrostatics, which dictates the pressure exerted by a fluid at rest. For a vertical column of water, the pressure is determined by its height multiplied by the density of the fluid and the acceleration due to gravity, leading to the familiar constant of 0.433 pounds per square inch per foot of elevation. This is why elevation changes, whether caused by the height of an elevated storage tank or the topography of a municipal main, must be factored into every hydraulic calculation. If you miscalculate the effect of a 50-foot elevation gain, you have already guaranteed a significant error in your residual pressure analysis. When water begins to flow, however, we move into fluid dynamics, where the Bernoulli equation becomes our most essential tool. This principle states that for an incompressible, non-viscous fluid in steady flow, the sum of pressure energy, kinetic energy, and potential energy remains constant throughout the system. Because real-world water distribution systems are not ideal, we must account for energy loss due to friction, which is where the Hazen-Williams and Darcy-Weisbach equations come into play. The Hazen-Williams formula is the industry standard for fire protection, as it empirically relates flow rate, pipe diameter, and the roughness coefficient to the pressure drop observed over a specific length of pipe. Choosing the correct C factor, which represents the internal smoothness of the pipe, is critical, as a corroded steel pipe will exhibit significantly more friction loss than a brand new cement-lined ductile iron pipe. Darcy-Weisbach is more physically rigorous and theoretically sound, particularly for fluids other than water or extreme flow regimes, and it relies on the friction factor derived from the Reynolds number. In complex piping geometries where you have elbows, T's, and various valves, we convert these physical components into equivalent pipe lengths to simplify the hydraulic modeling process. Managing these calculations correctly is the difference between a compliant system and one that lacks the necessary volume and pressure at the most remote sprinkler head. Field verification usually involves flow testing, where we measure the static pressure, the residual pressure, and the pilot pressure during a controlled discharge from a hydrant. The pitot tube, when inserted into the stream of the flowing water, measures the velocity pressure, which allows us to calculate the actual flow in gallons per minute. By plotting these test results on semi-logarithmic paper, we create a hydraulic graph that represents the available water supply curve for that specific location. We then compare this supply curve against the system demand curve, which represents the amount of water required by our fire protection system at a specific design pressure. If the water supply curve is not sufficiently above our demand curve at all points, the system is fundamentally flawed and requires intervention. This intervention could involve upsizing the underground mains, installing a fire pump to boost pressure, or seeking alternative sources like on-site gravity tanks or pressurized reservoirs. The capacity of these secondary sources must be calculated with extreme care, particularly regarding drafting operations where the lift distance and pipe diameter significantly restrict efficiency. You must ensure that these tanks are sized to support the full duration of a fire event while accounting for factors like evaporation and the minimum water level requirements for vortex prevention. Regulatory compliance further dictates that these systems must be reliable and redundant, meaning you cannot rely on a single, vulnerable supply point for a critical facility. Whether you are dealing with a simple loop system or a complex mesh grid, the goal remains the same. The system must deliver the required water volume at the correct pressure during the peak demand phase of the suppression system operation. Taking the time to perform these exhaustive manual checks ensures that your design is not based on optimistic assumptions, but on the raw reality of physics and hydraulic constraints. See you in the next lecture. Welcome to this chapter on fire pump sizing, where we will dive into the technical engineering requirements for stationary fire pump systems. In this series of lessons, we are going to unpack the rigid engineering standards required for the design and specification of stationary fire pumps according to NFPA 20. If you are serious about passing the CFPS exam, mastering these hydraulic principles is non-negotiable, because this is where design theory meets actual field reliability. Our curriculum focuses on the practical application of horizontal split case, vertical inline, vertical turbine, and in-suction pumps, ensuring you can identify the right tool for the right hydraulic demand. We will move beyond the basics by analyzing performance curves, churn pressure limitations, and the critical thresholds at 150% flow. By the end of this module, you will have a rock-solid understanding of how these mechanical systems interact with complex building architectures and life safety requirements. This level of detail is exactly what you need to distinguish yourself as a fire protection specialist who understands the mechanical backbone of water-based suppression systems. When we approach fire pump sizing, we must first establish the required fire demand, which involves summing up the sprinkler system demand plus the required hose stream allowance mandated by the relevant NFPA installation standard. This total flow and pressure requirement dictates the performance characteristics of the pump. A pump is not chosen based on a single point of operation, but rather its ability to traverse a performance curve that starts at churn, which is zero flow, and extends to at least 150% of the rated capacity. At the churn point, the pump must not exceed 140% of the rated pressure, a constraint that exists to protect the downstream piping network from overpressurization during low-demand events. Conversely, at 150% flow, the pump must be capable of delivering at least 65% of its rated pressure to ensure that high-velocity fire suppression requirements are met during an actual, massive fire event. These 3 points, churn, rated flow, and 150% flow, are the anchors of pump selection and verification. Perhaps the most neglected aspect of pump design is net positive suction head, or NPSH, which is fundamentally a measure of the absolute pressure at the suction flange. If the available NPSH drops below the required NPSH of the pump, we encounter cavitation, which is the formation and subsequent collapse of vapor bubbles within the pump housing. This phenomenon is destructive, leading to pitting of the impeller, extreme vibration, and a catastrophic loss of hydraulic performance. To calculate this, one must account for the atmospheric pressure, the static lift, or head, and the friction losses in the suction piping while subtracting the vapor pressure of the water. Ensuring the pump has a flooded suction, where the water source is located above the pump centerline, is the most effective way to eliminate these suction side pitfalls. In scenarios where a vertical turbine pump is deployed in an underground reservoir, we are effectively utilizing a column-supported impeller design to satisfy these hydraulic requirements from the bottom up. Beyond the pump itself, the driver, whether electric motor or diesel engine, must be sized to handle 100% of the pump's brake horsepower at any point on the performance curve. We often overlook the fact that a fire pump can experience a runaway flow condition, which shifts the motor toward its maximum power output. Therefore, the driver must be non-overloading at any point. Electric motor controllers and diesel engine controllers must be listed for fire pump service to ensure that essential electrical supply circuits remain energized even when other building systems are tripped. We must also integrate the sensing line, which provides the critical feedback loop to the controller by monitoring discharge pressure, and it must be installed with independent connections to the discharge piping to prevent false signals. Should a failure occur, the bypass arrangement, if required by local jurisdiction, allows for manual intervention or provides an alternate path for water flow during maintenance. Complexity of these systems increases significantly when we introduce high-rise zoning or series arrangements where multiple pumps are staged to overcome significant gravitational head. In such configurations, we must carefully manage the pressure at each zone so that we do not exceed the pressure ratings of the sprinkler components installed on the lower floors. This requires meticulous attention to the placement of relief valves, which act as a fail-safe to bleed off excess pressure if the pump drifts away from its design point. Furthermore, the test loop is not just an optional component. It is a mandatory requirement for verification that the pump can actually hit its performance targets during the annual inspection and testing cycle. By maintaining these rigorous installation and maintenance protocols, we ensure that the mechanical response is instantaneous and that the hydraulic integrity of the fire protection system remains steadfast under the most severe conditions imaginable. I will see you in the next lecture. Welcome back to our exploration of active fire suppression technologies. In this session, we will deep dive into the design and hydraulic requirements of wet pipe automatic sprinkler systems. Wet pipe systems represent the most common and reliable form of automatic fire suppression in commercial environments. At the core of their design is the principle of constant water pressure within the piping network, held back by a thermally sensitive sprinkler head. When the temperature at a specific head reaches its activation threshold, the heat-sensitive element breaks or melts, allowing water to discharge directly onto the ignition source. Unlike dry systems that rely on pressurized air or nitrogen, the wet pipe system provides near instantaneous water delivery, which is why it is preferred wherever freezing conditions are not a concern. From a design perspective, we must categorize the occupancy based on its fire hazard potential, which then determines the required water density and the design area for our hydraulic calculations. Understanding the hazard classification is your first step in determining the flow requirements for a project. NFPA 13 classifies spaces into light hazard, ordinary hazard, and extra hazard, each with distinct fuel loads and growth rates. For a light hazard occupancy like an office, the expected heat release is relatively low, while extra hazard classifications, such as those found in manufacturing or processing facilities, require significantly higher water densities to achieve suppression or control. We map these classifications to density area curves, which provide the minimum required water flow in gallons per minute per square foot over a specific design area. You must balance these requirements with the hydraulic capabilities of the water supply to ensure that the most remote sprinkler, often called the hydraulically demanding head, receives sufficient pressure. When we inspect sprinkler head technologies, it is helpful to view them as a component with specific performance characteristics. The response time index, or RTI, defines how quickly the thermal element reacts to heat, which is critical for early suppression or control. We also use the K factor to calculate discharge. This value represents the orifice size of the sprinkler and determines how much water flows at a given pressure. If you increase the pressure at a sprinkler, the flow rate increases according to the square root of that pressure. You must also consider spray patterns and coverage areas, as the orientation of the deflector determines the distribution of the water plume. If an obstruction blocks the spray, the suppression effectiveness drops, necessitating specific placement rules for how close a sprinkler can be to walls, partitions, or structural elements. Design techniques range from traditional pipe schedules to complex hydraulically calculated networks. While pipe schedule methods were historically common for smaller projects, they are largely obsolete due to their inefficiencies. Modern practice relies heavily on node analysis, where we model the pipe network as a series of connected points to solve the Darcy-Weisbach or Hazen-Williams equations for friction loss. Whether you are designing a tree, grid, or looped system, the objective is to ensure that the piping layout maintains the required pressure at every sprinkler head. Gridded systems, in particular, offer efficient water routing by providing multiple flow paths, which reduces friction losses significantly compared to tree systems. However, this complexity requires greater rigor in hydraulic software modeling to ensure that the water delivery is uniform across the entire design area. Ancillary equipment is just as vital as the piping layout itself. The alarm check valve serves as the physical boundary that keeps the piping pressurized while simultaneously triggering an alarm when water flows through the system. We integrate water flow indicators to monitor specific zones and tamper switches on control valves to provide continuous supervision of the system state. In seismically active areas, bracing requirements become a primary design constraint, forcing us to account for lateral and longitudinal pipe movement. Furthermore, corrosion mitigation has become a major focus, as internal pipe decay can clog small orifices and ruin the effectiveness of the entire system. You must consider these factors as an integrated whole rather than treating them as separate components to design a resilient and compliant system. See you in the next lecture. Welcome back. In this lesson, we will examine the mechanical and hydraulic engineering principles governing dry pipe and pre-action sprinkler systems. Dry pipe systems serve as the primary defense in environments where ambient temperatures are insufficient to prevent the freezing of water-filled pipes. Unlike wet systems, the piping network downstream of the dry pipe valve contains compressed air or nitrogen rather than water. When a sprinkler head fuses, the sudden drop in pressure causes the dry pipe valve to trip, introducing water into the system. The fundamental challenge here lies in the time delay caused by the necessity of exhausting this compressed gas before water can reach the discharging sprinkler. This delay is directly proportional to the volumetric capacity of the system piping and the reliability of the air maintenance device. As a professional, you must understand that the differential between the air pressure and the water supply pressure is the key mechanism keeping the valve closed until the detection of a fire-induced pressure loss. Physics dictates the behavior of the compressed gas, and accurate calculation of the trip pressure ratio is non-negotiable for system compliance. To expedite the water delivery process in large systems, engineers frequently rely on quick-opening devices, such as accelerators or exhausters. An accelerator senses the initial rate of pressure decay and triggers the relaying of the dry pipe valve, essentially bypassing the time required for the air to travel back to the valve assembly. Exhausters provide a similar function, but work by venting the air directly to the atmosphere once a preset pressure threshold is reached. These devices are mechanical in nature, but they require periodic testing to ensure diaphragms and linkages remain responsive under long-term conditions. Failure to maintain these components can lead to a significant increase in the water delivery time, potentially compromising life safety objectives in large warehouse or cold storage occupancies. Pre-action systems offer a more nuanced approach, specifically designed for occupancies where the risk of accidental water discharge is unacceptable, such as server rooms or industrial high-value storage. These systems are categorized as non-interlock, single interlock, or double interlock, based on the complexity of their release mechanism. In a single interlock system, the valve opens upon the activation of a smoke or heat detection device, independent of the sprinkler heads themselves. A double interlock configuration adds an extra layer of security by requiring both an automatic detection signal and the physical operation of a sprinkler head before water is admitted into the piping. This dual requirement design creates a redundant safety barrier that prevents damage from mechanical impact or accidental damage to the sprinkler system. Understanding the logic gates of these systems is crucial because the performance requirements depend entirely on the interaction between the electrical detection circuit and the mechanical valve assembly. Maintaining the integrity of these systems involves rigorous attention to installation details, such as piping pitch and condensate management. Because dry air contains minimal moisture, the potential for internal corrosion is often underestimated until it results in blockages. Microbiologically influenced corrosion, commonly known as MIC, flourishes in the presence of stagnant water or localized condensation that accumulates in low-point pockets. Requiring a consistent downward pitch toward drains ensures that any internal moisture is removed during routine maintenance, thereby mitigating the risk of material degradation. Furthermore, specialized dry pendant heads are required to ensure that the drop assembly remains dry, right up to the seat of the sprinkler. If these specific components are not used, or if the pitch is insufficient, water will pool at the drop, freeze, and potentially cause catastrophic pipe failure or obstruction during an emergency event. The hydraulic complexity is further compounded when considering transient effects during the filling process. As water replaces the gas, the system enters a two-phase flow state that creates unique friction and surge conditions throughout the piping network. Calculating the water delivery time requires precise data on the total volume of the piping and the discharge capacity of the valve. If the water fails to discharge within the time limits prescribed by NFPA 13, the system may require additional quick-opening devices or an adjustment in the pipe internal diameters. These calculations are not merely academic. They define the performance limit of the protection strategy for the facility. Always evaluate the gas-to-water pressure ratios during your design phase to ensure the valve will actuate correctly under the specific supply constraints of the site. See you in the next lecture. Welcome to this opening chapter on the design and application of standpipe networks. We will examine the hydraulic, architectural, and tactical requirements that transform a basic pipe network into a life-saving infrastructure for manual firefighting. In this module, you will gain the specialized knowledge required to categorize, design, and verify standpipe systems in complex environments. We will move beyond general principles to master the specific hydraulic calculations needed to ensure that water arrives at the most remote hose connection with sufficient pressure to suppress fire, while simultaneously avoiding pressures that could compromise the integrity of firefighting equipment or user safety. By the end of this curriculum, you will possess the expertise to distinguish between system classes, evaluate pump integration, and navigate the challenges posed by super high-rise structures where verticality presents unique physical hurdles. The material is structured to bridge the gap between theoretical fire protection and the reality of field engineering, giving you the tools to excel on your exam. If you care about building systems that actually perform when they are needed most, this is the essential knowledge you have been seeking. To understand standpipe systems, we first have to appreciate their primary role as the backbone of manual firefighting in large or multi-story structures. A standpipe network is essentially a vertical extension of a building's water supply, designed to provide water at strategic locations to allow firefighters to attack a fire without needing to drag hoses from the ground level. We categorize these systems into three main classes, starting with Class 1, which is intended for utilization by trained fire department personnel and requires 2.5-inch hose connections. Class 2 systems are designed for use by building occupants and typically utilize smaller 1.5-inch hoses, whereas Class 3 systems serve a dual purpose by providing both the higher flow capabilities of a Class 1 system and the smaller hose connections for immediate, albeit limited, occupant response. These systems must also be classified by their water supply status, ranging from automatic systems, which are permanently connected to a water supply capable of delivering the required flow, to manual dry systems, which require an external water source to be coupled to the fire department connection. Designing these networks requires careful accounting for friction loss, elevation head, and the inherent variability of building geometry. The most critical aspect of your design process involves identifying the hydraulically most remote hose connection, which determines the minimum pump pressure required for the entire network. You must calculate the flow requirements at this point, typically dictated by code, to ensure a specific volume at a predetermined pressure, such as 100 pounds per square inch at the outlet. Once the remote connection is satisfied, we must account for the pressure losses that occur as water travels through the piping, fittings, and check valves. In modern high-rise buildings, this often creates a scenario where the pressure at lower floors would exceed the safe operating limits for standard hose nozzles if not regulated. This is where pressure regulating devices and master pressure reducing valves become essential, as they allow us to throttle excessive pressure down to manageable levels without starving the higher elevation connections. You cannot simply build a tall riser and pump the hell out of it, because the resulting hydrostatic pressure at the bottom would likely lead to pipe fatigue, burst joints, or an inability for a firefighter to hold the nozzle. Spacing and placement are equally important to the hydraulics because a system is only useful if it is accessible to the personnel who need it. Code requirements typically dictate maximum travel distances to hose valves, ensuring that a firefighter can reach any part of a floor level with a standard length of fire hose. These valves must be located in protected stairwells or designated areas of refuge to ensure they remain accessible even during an active fire situation. Furthermore, the fire department connection, or FDC, must be positioned where it is easily identifiable and accessible to the responding fire department, often requiring proximity to a public street and clear signage that remains visible even in low light conditions. The integration of these components requires a meticulous approach to bulk runs, as the piping must be routed to avoid structural hazards while maintaining enough flexibility to withstand thermal expansion and building movement. Every piping segment must be documented and verified to ensure that the actual installation matches your theoretical model. In dealing with super high-rise buildings, the complexity increases logarithmically due to the need for multiple pressure zones and express mains. A single riser column cannot service a skyscraper because the pressure demand at the base would necessitate pipe schedules and pump ratings that are practically and economically unfeasible. Instead, we divide the building into vertical zones, using intermediate fire pumps or pressure-reducing stations to bridge the gap between these zones. Express mains act as the heavy-duty feeders that move large volumes of water from the main fire pump room directly to the upper zones, bypassing the friction losses inherent in smaller, floor-by-floor branch piping. You must understand how these components interact with the building's fire pump capacity, as the pump must be sized not just for the peak hydraulic demand, but for the reliability and redundancy requirements mandated by safety codes. Ensuring that firefighters have the tactical pressure they need at every elevation remains the ultimate goal of your engineering work. I will see you in the next lecture. Welcome back, and today we begin our deep dive into special hazard suppression systems. This chapter will provide the technical expertise required to master suppression strategies for environments where traditional water systems fail. In industrial or high-tech spaces, water is often a liability rather than a solution, leading us to rely on clean agent systems. These agents, whether halocarbon compounds or inert gases like Ig541 and Ig55, function by disrupting the chemical chain reaction of fire or by reducing oxygen levels below the threshold of combustion. When evaluating these systems, you must move beyond basic coverage and focus on the enclosure integrity. An enclosure must be sufficiently airtight to maintain the required design concentration for the specified holding time, which is validated through door fan testing. If the enclosure lacks integrity, the agent will leak, causing the concentration to drop prematurely and allowing the fire to reignite. Furthermore, the rapid discharge of gaseous systems creates pressure differentials, necessitating the installation of peak pressure relief vents to prevent structural damage to the enclosure walls. Hydraulic flow calculations represent the most critical technical barrier in gaseous system design, as discharge nozzles are engineered for precise flow rates regardless of their distance from the agent supply. These calculations ensure that the agent remains in a liquid or gaseous state throughout the piping network until it reaches the discharge point, where nozzle orifice geometry manages the expansion. Unlike water-based systems, these gaseous systems rely on the specific density and vapor pressure of the agent, making the piping internal diameter and elevation changes vital variables. Designers must strictly adhere to NFPA 2001, ensuring that the piping integrity supports high-pressure discharge. Failure to account for the specific agent properties will lead to improper mixing within the room, leaving pockets of unsuppressed hazards that could permit fire growth despite the system activation. When addressing flammable liquid hazards, we shift our focus to foam suppression systems, which are classified by their expansion ratios into low, medium, and high application categories. The physical principle here involves blanketing the fuel surface to exclude oxygen and provide a cooling effect that prevents the release of flammable vapors. Proportioning equipment, such as bladder tanks or balanced pressure proportioners, must maintain a consistent foam-to-water ratio across varying flow demands, which is a common point of failure in field audits. You must calculate the application rate based on the specific fuel type, as polar solvents and hydrocarbons react differently to the chemical surfactants within the foam concentrate. The volume of foam generated must be sufficient to achieve total containment within the drainage path of the protected space, ensuring the fuel is physically isolated from the combustion air, regardless of spill size. Carbon dioxide suppression systems introduce a unique set of hazards because they extinguish fires by total flooding at concentrations that are inherently toxic to humans. This creates an immediate mandate for strict life safety lockouts and sophisticated interlock controls in any occupied facility. When planning CO2 systems for deep-seated fires, the design concentration must be maintained significantly longer than for surface fires, because the agent must penetrate porous materials to extract latent heat. Unlike clean agents, CO2 is often stored as a cryogenic liquid, requiring specialized insulation for high-pressure piping. You must treat the design of these systems as a closed-loop engineering problem where human life, equipment protection, and fire dynamics are weighed against the severe risk posed by the extinguishing medium itself. Water mist technology serves as an intermediate solution, bridging the gap between traditional sprinklers and gas-based systems by exploiting the latent heat of vaporization. These systems discharge extremely fine water droplets, giving the spray a massive surface area that absorbs thermal energy rapidly while simultaneously displacing oxygen with expanding water vapor. The performance of these systems is tied heavily to the nozzle geometry and the sustained system pressure, which must be high enough to produce the desired drop size distribution. Because mist systems operate at much lower water volumes than traditional sprinklers, they provide significant benefits in environments where sensitive water damage is a concern, such as archives or machinery spaces. Mastering these systems requires an intimate knowledge of how droplet diameter influences effectiveness, as the physics of energy absorption depends entirely on creating an environment that inhibits combustion at the microscopic level. See you in the next lecture. Welcome back to our technical exploration of fire alarm systems, where we will specifically examine the physical and operational principles of modern smoke detection technologies. This chapter provides an exhaustive analysis of sensing mechanisms and the strategic deployment strategies necessary for effective fire protection in complex environments. To understand smoke detection, we must first look at the underlying physics of particulate sensing. Ionization detectors rely on a radioactive source, usually americium-241, to ionize the air within a sensing chamber, creating a small electrical current. When smoke particles enter this chamber, they attach to the ions, reducing the current and triggering an alarm. While effective for detecting smaller, invisible combustion products from fast-flaming fires, these devices have specific limitations concerning high airflow environments. Conversely, photoelectric detectors utilize a light source and a photosensitive sensor arranged so that light does not normally strike the sensor. When smoke enters the chamber, light scatters off the particles and onto the sensor, which then initiates an alarm signal. This technology is inherently better at detecting larger, visible particles produced by smoldering fires, making it a critical component in balanced protection strategies. Beyond point-type detectors, we encounter light obscuration and air sampling systems that offer distinct advantages in specialized scenarios. Beam detectors operate on the principle of light attenuation, where a beam is projected across a protected space, such as an atrium, to a receiver that monitors the intensity of the light. If smoke enters the beam path, it obscures the signal, triggering an alarm once the obscuration reaches a preset threshold percentage. Aspirating smoke detection, or ASD, takes this a step further by actively drawing air samples through a network of pipes to a centralized sensing unit. This allows the system to detect incredibly low concentrations of smoke, making it indispensable for mission-critical facilities like data centers, where early, incipient stage detection is vital. Because these systems sample air directly, they are largely unaffected by thermal stratification, which often prevents smoke from reaching ceiling-mounted sensors in high-ceiling environments. Successful deployment is rarely just about the device hardware. It is about accounting for the fluid dynamics of the building itself. Smoke behavior is heavily influenced by thermal stratification, where a layer of hot gas forms beneath the ceiling, creating a thermal barrier that may prevent smoke from buoying upward to triggers. Furthermore, the presence of forced air ventilation systems can significantly alter smoke plume trajectories, dragging smoke away from detectors or diluting its concentration below threshold levels. We must design for these variables by carefully choosing detector spacing and placement according to NFPA 72 requirements. In ductwork, we utilize dedicated duct smoke detectors not necessarily to protect the building, but to provide a signal to the fire alarm control unit to initiate HVAC shutdown. This prevents the mechanical systems from acting as a distributed network for smoke and toxic gas throughout the entire structure. Modern systems frequently employ multi-criteria detection algorithms to handle the persistent challenge of nuisance alarms. By integrating inputs from photoelectric ionization and thermal sensors, these systems can analyze the signature of the air in real time to distinguish between hazardous smoke and common contaminants like steam, dust, or cooking aerosols. These digital signal processing techniques allow for a much higher immunity to false triggers without sacrificing the speed of response during an actual fire. However, the integrity of these systems relies entirely on periodic testing protocols mandated by code to ensure that sensitivity calibration remains within manufacturer specifications. We must treat these environmental and technological variables as a cohesive system rather than individual components if we want to ensure reliable performance during an emergency. By meticulously aligning the sensing technology with the architectural demands of the occupancy, you ensure that the detection system provides the highest possible level of life safety. See you in the next lecture. Welcome to our exploration of heat detection systems, where we will examine the precise mechanisms that trigger life safety responses in environments where traditional smoke detection fails. In industrial or manufacturing settings, the presence of airborne particulates, steam, or extreme temperature fluctuations often renders ionization and photoelectric smoke sensors ineffective due to frequent false alarms. Heat detection serves as the primary alternative, functioning on the fundamental principles of thermodynamics rather than obscuration. These systems are categorized primarily by their thermal response characteristics, specifically fixed temperature operation and rate of rise detection. A bimetallic element operates by exploiting the differing coefficients of thermal expansion between two bonded metals, which causes the element to deflect and close an electrical circuit once a predetermined temperature threshold is reached. Alternatively, fusible alloys utilize materials with precise melting points, such as eutectic solders, which transition from solid to liquid states to release a contact or a sprinkler bulb at a calibrated temperature. Understanding these material properties is essential for selecting the correct sensor for a given industrial process. Moving into more sophisticated diagnostic territory, we must consider the rate of rise technology, which monitors the velocity of temperature escalation rather than just the absolute temperature. These detectors typically utilize pneumatic principles, where air trapped in a chamber expands as it heats, causing a diaphragm to depress electrical contacts. Modern iterations employ thermistors, which are semiconductors that demonstrate a sharp change in electrical resistance as they heat up. The advantage here is the ability to detect a rapid fire development even before the ambient temperature reaches a fixed temperature trigger point. When designing for expansive areas like warehouse logistics, conveyor belts, or subway tunnels, point detection becomes impractical. In these scenarios, linear heat detection cables or distributed temperature sensing utilizing fiber optics are employed. These technologies provide continuous monitoring along specific paths, allowing the fire alarm control unit to pinpoint the location of the heated section based on electrical impedance or calibrated light scattering analysis. Strategic placement and performance modeling represent the most critical components of your professional assessment of these systems. The performance of a heat detector is mathematically dependent on the response time index, which characterizes the sensitivity of the sensor relative to the thermal inertia of its sensing element. We calculate the thermal lag by factoring in the gas temperature and the velocity of the fire plume at the ceiling level. As the ceiling height increases, the buoyant plume loses energy through entrainment, meaning the detector must be spaced more tightly to compensate for the cooling effect of mixing with ambient air. Structural geometry, such as beams or varying roof pitches, forces us to apply specific reduction factors to the standard spacing guidelines found in NFPA 72. You should always look at the fire growth curve, often squared as t-squared models, to estimate how quickly the heat will breach the activation threshold of the selected device. Finally, you must navigate the constraints of hazardous environments where electrical energy could inadvertently trigger an ignition event. In these locations, thermal sensors must be rated as explosion-proof, meaning they are designed to contain an internal explosion without propagating a flame front to the surrounding atmosphere. For areas where gases or vapors are present, intrinsically safe circuits are required, limiting the electrical energy to levels insufficient to ignite the ambient hazard even under fault conditions. These sensors often integrate directly with deluge or pre-action suppression systems, where the heat detection logic serves as the initial release trigger. The complexity of these systems necessitates a thorough understanding of signal processing, as you are responsible for ensuring detection integrity even when ambient temperatures approach the threshold of the sensor. The design must be robust, survivable, and perfectly integrated into the broader fire protection strategy for the facility. I will see you in the next lecture. Welcome to our deep dive into flame detection methods, where we examine the technical nuances of radiant energy sensing. In this lesson, we will dissect the specific technologies that allow us to detect flaming combustion the instant it occurs in complex, high-hazard environments. To understand modern flame detection, we must first focus on how these devices interact with the electromagnetic spectrum. Ultraviolet and infrared sensors are the primary tools in our arsenal, each sensitive to specific wavelengths emitted by a combustion process. When a fuel burns, it produces a spectral signature that is unique to the chemical reaction taking place. Ultraviolet detectors are engineered to be solar blind, meaning they disregard the ambient sunlight that reaches the Earth's surface, which would otherwise trigger false alarms. This is achieved by limiting the sensitivity to the 185 to 260 nanometer range, where atmospheric ozone naturally absorbs solar radiation. By isolating this narrow band, the sensor specifically targets the ionizing radiation associated with the early stages of a flame, providing a highly reliable detection method in clean environments where interference is minimal. Infrared sensors, on the other hand, operate by detecting the thermal radiation emitted by carbon dioxide molecules in the flame. As a hydrocarbon fuel burns, the combustion process excites the CO2 molecules, resulting in resonance spikes at specific infrared wavelengths, typically around 4.3 micrometers. This is a robust method because flames of this type will always produce this specific signature, regardless of the ambient air temperature or the presence of other heat sources. However, the challenge arises when we must distinguish this target signal from non-fire sources like hot surfaces, heaters, or general blackbody radiation. To solve this, manufacturers often employ multi-spectrum infrared sensors that analyze multiple wavelength bands simultaneously to correlate the specific CO2 emission with the flickering patterns characteristic of fire. This mathematical comparison allows the processing algorithm to filter out stationary heat sources that lack the dynamic signature of a growing flame. Integration of these technologies into dual-spectrum devices essentially provides the best of both worlds, combining the speed of ultraviolet detection with the false alarm immunity of infrared. When we deploy these in high-hazard areas like petrochemical facilities or hangars, we must be mindful of signal attenuation, which is governed by the inverse square law. As the distance between the fire and the sensor increases, the intensity of the radiant energy falling on the detector decreases proportionally to the square of that distance. This means a sensor has a fixed, finite field of view and range, and simply mounting it on a wall is rarely sufficient for complex geometries. We must consider the cone of vision to ensure that there are no obstructions, such as structural beams or heavy equipment, that could mask a developing fire from the sensor's line of sight. Optical integrity monitoring is another critical aspect that separates professional-grade systems from simple, off-the-shelf components. Many modern detectors include internal testing routines that periodically verify the cleanliness and functionality of the optical window. If dust, oil, or chemical spray accumulates on the lens, the system reports a fault, ensuring that the sensor does not lose its ability to see the hazard. This is particularly vital in munitions storage or aircraft maintenance where the environmental conditions can change rapidly. By meticulously calculating the installation geometry, account for spectral signatures, and implementing automated testing, we create a robust detection network that is far more reliable than standard point-based smoke detectors in these specific high-energy fire scenarios. I will see you in the next lecture. Welcome back. In this chapter, we explore the engineering requirements for notification appliance circuits, moving from basic signaling to complex life safety architectures. Notification appliance circuits, or NACs, represent the delivery mechanism for fire alarm signaling within a structure. These circuits bridge the gap between the fire alarm control unit and the physical devices intended to alert occupants during an emergency. In a purely technical sense, an NAC is an electrical pathway monitored for integrity, meaning the system continuously checks for physical breaks or shorts that might prevent a signal from firing. When we look at the wiring topologies, we often distinguish between Class A and Class B configurations. Class A circuits utilize a return loop to the control panel, ensuring that even with a single break in the wire, signals can still propagate. Class B circuits are simpler in design, but rely on an end-of-line resistor to maintain constant supervision of the entire circuit length. Understanding the nuances of these configurations is essential for maintaining the operational survivability of fire alarm systems in demanding environments. The physics governing these circuits is dominated by the reality of voltage drop over distance. Since fire alarm devices are typically powered by low-voltage Drell sources, The resistance inherent in the copper wiring causes a reduction in potential as the signal travels away from the source. To calculate this, we use the basic relationship between current, resistance, and wire gauge, ensuring that the last device on a circuit still receives the minimum operating voltage required by its listing. If the voltage drops below this threshold, the notification appliance may fail to activate or, worse, provide an intermittent or low decibel alert. Furthermore, when we incorporate strobe lights into these circuits, we must account for the capacitive load they introduce, which can severely distort the electrical pulse if not carefully calculated against the panel's power limits. Proper wire gauge selection is not merely a suggestion, but a required exercise in load balancing for any certified professional. Acoustic engineering within fire alarm systems requires a solid grasp of sound pressure levels and ambient noise environments. We measure sound in decibels, often utilizing the A-weighted scale to reflect human hearing sensitivity, which is why we must ensure our alarms provide a specific decibel surplus above the prevailing ambient noise level. In public mode, such as in schools or offices, that surplus is typically 15 decibels over the average ambient sound or 5 decibels over the maximum sound that lasts longer than 60 seconds. Private mode, conversely, allows for lower thresholds if the occupants are trained staff who will immediately act upon the alarm signal. We must also account for distance attenuation, where sound intensity decreases according to the inverse square law as it spreads through the space. Achieving this balance requires careful placement of sounders to avoid dead zones while ensuring areas intended for sleeping receive the specific 520 Hz low-frequency temporal 3 signal required to penetrate deep REM sleep. Strobe light synchronization serves as a vital mitigation strategy for occupants prone to photosensitive seizures. When multiple strobes are located within the same field of view, it is mandatory that they flash in tight synchronization to prevent the cumulative effect of disparate flashes. From a design perspective, this necessitates that the control panel or the appliances themselves possess a timing protocol that maintains a consistent flash rate and phase. Beyond synchronization, we must select candela ratings based strictly on the room geometry and the viewer's orientation to the device. Indirect viewing strategies are common in corridor or large room designs, where high-output strobes bounce light off wall surfaces to provide uniform coverage without overwhelming occupants. This engineering rigor ensures that the notification system remains a life-saving tool rather than an additional hazard during an already dangerous fire event. See you in the next lecture. Welcome back, everyone. Today, we are delving into the architecture and operational logic of fire alarm control units. The Fire Alarm Control Unit, or FACP, acts as the central brain of any life safety installation, coordinating inputs from initiation devices and dispatching signals to notification appliances. In conventional systems, the architecture relies on zone detection, where a circuit is populated with devices that trigger a common alarm for a specific area, lacking granular identification of the exact offending device. This approach is conceptually simple, but presents limitations in large-scale facilities where pinpointing an emergency is critical for rapid first responder intervention. Conversely, intelligent addressable systems utilize a signaling line circuit, commonly referred to as an SLC, which employs digital communication protocols to interrogate individual devices. Each detector or module on an SLC has a unique physical address, allowing the FACP to monitor the health, status, and precise location of every component on the loop through continuous polling algorithms. When we examine the logic governing these units, the transition from simple binary status reporting to complex matrix programming represents a significant leap in system sophistication. Modern panels allow for cross-zoning, a logic sequence where the FACP only initiates a general alarm or suppression release once 2 or more separate detectors confirm an event, thereby mitigating the risk of inadvertent nuisance alarms. Furthermore, the positive alarm sequence feature introduces a predefined investigative delay, granting trained personnel a window of time to verify the incident before the building-wide notification sequence commences. This logic is further extended through cascading programming, where various input scenarios trigger distinct output matrices. These matrices dictate the state of auxiliary relays, which facilitate critical building control functions such as elevator recall, the positive latching of electromagnetic door releases, and the shutdown or repositioning of HVAC dampers to manage smoke migration. Power supply management remains a cornerstone of FAP reliability, as the system must remain functional during primary power failures. NFPA 72 mandates specific battery capacity requirements, requiring the system to operate under its quiescent load for a set duration, often 24 hours, followed by a full alarm load for a minimum of 5 to 15 minutes depending on the occupancy type. Engineers must account for battery derating factors, which include the ambient temperature effects on lead-acid chemistry and the aging process that gradually reduces the total amp-hour capacity of the backup supply. While some installations utilize uninterruptible power supply topologies for additional stability, the primary battery backup must remain independent and directly supervised by the panel software to ensure it is ready for demand. Accurate calculation of these standby requirements prevents the common pitfall of a system failing to sustain its signaling capability during an actual extended power grid disruption. Communication to the outside world is equally vital, as the FACP must reliably transmit event data to a supervising station through diverse pathways. Digital Alarm Communicator Transmitters, or DACTs, have traditionally relied on standard telephone lines, but contemporary standards demand more robust and redundant transmission technologies. Today, IP communicators and cellular mesh networks are standard, providing multiple paths that bypass the single points of failure inherent in older copper line systems. For proprietary supervising stations that monitor massive distributed campus environments, the requirements extend to stringent physical survivability and cybersecurity protocols to protect against both intentional tampering and natural disaster damage. By isolating the internal network traffic and using encrypted signaling, these systems ensure that the integrity of the life safety information is maintained from the moment a trigger occurs at the device level until the alarm signal is acknowledged by a remote operator. See you in the next lecture. Welcome to the chapter on voice communication systems, where we will translate building notification requirements into reliable engineering practices. By the end of this module, you will understand how to design and audit systems that guide occupants to safety during complex emergencies. Emergency voice alarm communication systems, or EVAC, represent a significant leap in complexity compared to simple horn strobe notification. When we talk about these systems, we are moving from basic alerting to authoritative command, which requires a rigorous approach to system architecture. The heart of any effective EVAC installation is the audio amplifier, which must be sized not just for the peak load of the installed speakers, but also to accommodate future expansion or the specific power requirements of high decibel zones. We often see practitioners make the mistake of failing to account for transformer insertion losses when calculating speaker tapping, which leads to degraded signal quality in outlying zones. A robust design ensures that every speaker, whether in a high-rise stairwell or an open-roof stadium, receives a consistent, clean signal that maintains the integrity of the life safety message throughout the entire facility. Survivability is a critical dimension of our circuit design, as we must assume that parts of the building will become untenable during a fire event. NFPA standards mandate that we provide redundant signal paths so that a single fault, whether it is a short circuit or a ground fault, does not result in the loss of communication to an entire floor or fire zone. This is achieved through Class A wiring configurations or sophisticated isolation modules that disconnect compromised branches of the audio circuit while keeping the rest of the network operational. We must also consider the physical protection of the cabling itself, ensuring it is routed through fire-rated enclosures or protected pathways that align with the specific hazard levels identified in the building's risk analysis. Designing for survivability means acknowledging that while the system must continue to function, the environmental conditions under which it operates will be rapidly deteriorating. Intelligibility is the primary metric by which we evaluate the success of our voice communication strategy. It is not enough to simply have an audible signal. We need a clear, actionable message that reaches the occupant, even amidst the chaotic noise of an unfolding emergency. We utilize the Speech Transmission Index as our quantitative benchmark for this clarity, measuring the degree to which speech signals are preserved across the acoustical landscape of the facility. Factors like reverberation time, which is heavily influenced by the volume of the space and the absorption coefficients of the interior surfaces, must be managed to prevent audio muddying. In large, hard surface spaces like warehouses or parking garages, we might need to introduce specialized acoustical treatments or adjust the density of the speaker placement to compensate for the lack of sound absorption. Ambient noise masking must also be considered, as the system must generate enough power to rise above the steady-state background noise while avoiding the creation of painful or distorted output. Beyond physical hardware, the programming logic of the system defines how the facility responds during a crisis. We are tasked with setting priorities for localized microphone paging, allowing fire marshals or facility managers to override automated digitized messages when specific, nuanced instructions are needed. These control units must be autonomous, maintaining the ability to command the building even if the connection to the main fire alarm control panel is interrupted. This decentralization of control provides a buffer against system-wide failures while ensuring that vital instructions can be delivered locally. Firefighter telephone systems extend this capability by allowing two-way communication between floor wardens and the primary command center. Properly integrated, these systems transform a static fire alarm installation into a dynamic management tool that can steer populations away from danger and facilitate a controlled, phased evacuation. See you in the next section. Welcome to this module on fire resistance rated construction, where we will examine the principles behind protecting structural integrity during fire events. We will systematically break down how buildings withstand thermal stress to ensure you are fully prepared for the certification examination. Fire resistance ratings serve as the primary defensive barrier in building design, essentially quantifying how long a structural element can maintain its load-bearing capacity and compartmentalization duty under a simulated fire exposure. When we look at standard testing methodologies like ASTM E119 or UL263, we are not looking at real-world fire scenarios, but rather a strictly defined time-temperature curve meant to provide a consistent benchmark for building materials. This curve represents a rapid heat intensity increase, pushing materials to their physical limits to see if they can prevent the passage of flame and hot gases while supporting their design load. An element's rating is expressed in hours, and achieving this rating requires a holistic understanding of how convective and conductive heat transfer impacts specific material science. We must recognize that the performance criteria differ slightly depending on whether the element is a column, a floor, or a load-bearing wall, though the fundamental requirement remains the preservation of structural stability and the mitigation of heat transmission. The physics of material degradation under severe thermal loading is a critical area of study for the practicing professional, particularly regarding how different building materials respond when subject to intense heat. Steel, for instance, loses its structural strength quite rapidly as temperatures rise, typically reaching a critical temperature where it can no longer support its required design load, necessitating the use of spray-applied fire-resistive materials or concrete encasement to delay this outcome. Concrete behaves differently, often suffering from internal vapor pressure buildup that leads to spalling, a condition where chunks of concrete break away from the surface and expose the internal reinforcement to the fire. Timber, while combustible, provides predictable performance through charring, where the outer layer burns away to create a protective, insulating barrier that slows the progression of heat into the remaining structural core. Intumescent coatings provide another layer of defense by reacting to heat through expansion, creating a thick, insular foam layer that shields the substrate from the rapid temperature rise that would otherwise result in catastrophic failure. When we approach the calculation of heat transfer through composite assemblies, we are essentially performing a thermal analysis of a multi-layered system designed to minimize the temperature rise on the unexposed face to a level that prevents autoignition of adjacent materials. This requires us to look at the thermal conductivity, density, and specific heat capacity of every component within the assembly, from the initial surface finish through the core insulation to the exterior structural skeleton. Analytical methods allow us to determine the resistance of an assembly without requiring the financial and time-consuming burden of full-scale fire testing, provided we have reliable laboratory data for the constituent materials. We focus on ensuring that the bonds between these materials remain intact, as any separation or failure of the fire-rated barrier allows thermal energy to bypass our protective strategy, potentially compromising the compartments we intended to secure. By mastering these analytical approaches, you gain the ability to verify that design specifications translate into actual field performance, which is an essential skill for any certified fire protection specialist working on sophisticated structural projects. See you in the next lecture. Welcome back. Today we examine the technical requirements for fire door and window assemblies within the scope of passive fire protection. Fire door assemblies represent a dynamic component of fire-rated construction that must maintain barrier integrity under extreme conditions. Unlike fixed walls, these assemblies must balance egress functionality with the requirement to resist fire, smoke, and heat transfer. When a building is subjected to a fire event, the door assembly acts as a critical seal, preventing the migration of toxic gases and thermal energy between compartments. The fundamental design philosophy relies on the assembly remaining closed and latched during the incident. We must understand that a fire door is not merely a door leaf, but a complete system consisting of the door, frame, hardware, and sealing elements. If any single component fails, such as a latch or an intumescent seal, the entire assembly may lose its fire rating. Maintaining this system requires precise adherence to listing and labeling protocols established by testing laboratories. Testing procedures for these assemblies involve rigorous exposure to standard fire tests, which often include both positive pressure and hose stream evaluations. Positive pressure testing is particularly significant because it simulates the actual pressure differentials generated by a compartment fire that forces hot gases through door gaps. During the furnace test, the assembly is subjected to a controlled thermal profile that measures heat transmission and structural integrity over time. Following the fire exposure, the hose stream test is conducted to ensure the assembly maintains its physical stability against the mechanical impact of firefighting water streams. For glazing materials, the thermal transmission criteria are equally stringent, as transparent materials must restrict the passage of heat to prevent ignition on the unexposed side. These standards ensure that doors provide a reliable duration of protection, typically ranging from 20 minutes to 3 hours depending on the fire resistance rating requirements of the partition. The mechanical anatomy of a fire door assembly governs its ability to function automatically when a hazard is detected. Standard swinging doors must be equipped with self-closing and self-latching hardware to ensure the opening remains secured without human intervention. Intumescent edge seals play a vital role here, as they expand when exposed to high heat to close the clearance gaps around the door perimeter. These gaps are subject to strict tolerance limitations because even minor excessive clearances can allow smoke infiltration. For sliding or rolling steel doors, the mechanism must be coupled with devices that ensure prompt closure upon activation. Astragals are utilized on pairs of doors to cover the meeting edge, ensuring that no direct path for heat or flame exists through the center of the opening. The physical interplay between these mechanical parts is what allows a fire-rated door to behave like a monolithic wall during a thermal event. Integrating electronic security and safety features into these assemblies requires close attention to the interface between hardware and the fire alarm system. Magnetic hold-open devices are commonly utilized for convenience, allowing doors to remain open during normal operations while ensuring they release instantly when a smoke detection array triggers an alarm. The reliability of this integration depends on the interaction between the detection signal and the release of the door closer, or electromagnet. It is imperative that these systems remain fail-safe, meaning that a loss of power or a malfunction in the detection circuit initiates the closing process. Furthermore, field inspection, testing, and maintenance protocols are established to ensure that these mechanical elements do not suffer from degradation over time. Inspectors must verify that clearances remain within the manufacturer's listing and that all door hardware operates smoothly without the need for excessive physical force. Proper maintenance is not just about functionality. It defines the ongoing effectiveness of the entire building compartmentation strategy. We often see issues where overpainting, improper field modifications, or sagging hinges compromise the assembly's ability to seal against smoke and flames. Field inspections serve as a final check to ensure that the assembly, in its installed state, matches the certified configuration tested in the laboratory. By scrutinizing the hardware, frame anchoring, and the door itself, we ensure that the passive fire protection system continues to provide the necessary life safety performance. We must treat these assemblies as living components of the safety system that require periodic verification to function flawlessly under extreme thermal distortion. This systematic approach ensures that firefighters and building occupants are shielded by effective barriers that have not been inadvertently bypassed by poor maintenance or unauthorized changes. I look forward to discussing the specifics of fire-stopping materials in our subsequent session. Welcome back. We are now narrowing our focus to the critical engineering challenges associated with maintaining compartmentation through fire-stopping materials application. When we discuss fire stopping, we are essentially talking about the integrity of the fire-rated barrier. Every time a building is constructed, we create structural breaches for mechanical, electrical, and plumbing systems. A fire-rated wall or floor is only as effective as its weakest point, which is often the interface between a service penetration and the building element itself. If we fail to seal these openings correctly, we allow for the vertical and horizontal propagation of flame and smoke, effectively neutralizing the safety objectives of our fire compartmentation strategy. Our task here is to understand the material science behind the solutions we employ to mitigate these risks. The materials we use are engineered to respond to fire under distinct thermodynamic principles. Intumescent sealants are perhaps the most common, designed to expand significantly when exposed to heat. This expansion seals the void left behind by combustible service pipes that have melted away during a fire event. You must distinguish these from endothermic materials, which chemically absorb heat energy to delay the temperature rise on the unexposed side of the barrier. Ablative coatings, on the other hand, function by shedding layers of material to dissipate energy through ablation, while elastomeric caulks provide the necessary movement capability for joints that must withstand thermal expansion or structural vibration. Understanding the physical behavior of these materials is not optional. It is the foundation of a robust installation. Testing and certification standards like UL 1479 and ASTM E814 provide the framework for how we quantify the performance of these systems. The F rating, or fire rating, tells us the duration the system remains in place before flame or hot gases pass through the assembly. However, the T rating adds a critical layer of data by measuring the temperature rise on the unexposed side, ensuring that the sealant does not conduct enough heat to ignite nearby combustibles. We might also see L ratings, which quantify air leakage rates, a vital statistic when you are dealing with smoke control systems. Finally, the W rating ensures that the system is resistant to water, which is often overlooked in exterior wall applications or areas prone to high moisture levels. The complexity increases when we consider the geometry of the breach. Through penetrations involving metallic or non-metallic pipes require precise annular space requirements, defined by the specific tested system. If the annular space is too tight, the material cannot be installed properly. If it is too wide, the material might not have sufficient structural support. This is where backing materials come into play, which must be compressed to the manufacturer's specification to ensure stability during the curing process. We must also consider the dynamic nature of movement joints. These joints are not static. They shift due to wind loads, temperature changes, or building settling. If the fire stopping system is not engineered for these specific movement parameters, the sealant will tear, eventually creating a failure point that defeats the entire barrier design. In engineering practice, we often encounter scenarios that do not exactly match a listed system in a directory. This necessitates the use of engineering judgments, or EJs, which are site-specific modifications based on established tested data. An EJ is not a guess. It must be signed by a licensed professional who can justify the variation based on the principles of fire resistance. Even with the perfect design and the most appropriate materials, the human element remains the greatest variable. We must account for installation tracking and mandate destructive verification in our quality assurance programs. Without these controls, the barrier's integrity relies entirely on the technician's accuracy, which is rarely an acceptable risk level for a high occupancy facility. See you in our next session. Welcome back. In this chapter, we explore the critical architectural and engineering strategies for building compartmentation, where we define the passive boundaries necessary to restrict fire and smoke migration. Successful compartmentation is essentially an exercise in geometric containment, where we leverage structural elements to buy time for occupants to exit and for tactical responders to perform their work. You might think of it as a logical separation of concerns within the building envelope, where each zone must be able to withstand the thermal and pressure loads imposed by a fire event. If we treat the building as a collection of isolated systems, our compartmentation strategy must ensure that a failure in one module, a room, or a floor does not lead to a systemic failure of the entire structure. The NFPA codes provide the rigorous definitions required to distinguish between firewalls, fire barriers, and fire partitions, each serving a distinct purpose based on the anticipated risk and occupancy classification. By mastering these distinctions, you move beyond mere compliance and begin to understand how the physical layout serves as the first line of defense against catastrophic loss. This is technical, foundational knowledge that every certified fire protection specialist must rely on daily. Firewalls are the most robust form of physical separation, designed to provide a complete structural break between buildings or to subdivide a massive building into separate, distinct entities. Unlike fire barriers, these walls must typically be constructed as independent structural assemblies that can survive the total collapse of the structure on either side. We often see these in large, complex facilities where we need to prevent the spread of fire from a high-hazard area to a low-hazard area without relying on active suppression systems alone. The code mandates that these walls extend from the foundation to or through the roof, often requiring parapets to prevent vertical flame spread over the top. When we calculate allowable floor area, these firewalls are our primary tool for essentially creating a new building on paper, effectively resetting the hazard area and permitting larger overall structures. They function as the ultimate boundary, and their integrity is non-negotiable under fire conditions. Fire barriers and fire partitions offer less structural independence but are equally vital for maintaining internal safety zones, such as exit enclosures or specific occupancy separations. A fire barrier is designed to limit the spread of fire and restrict movement, and it must reach from the floor slab to the underside of the floor or roof deck above. Think of these as the vertical partitions that slice through the floor plan to isolate hazardous processes, mechanical rooms, or stairwells. Fire partitions, by contrast, generally offer a lower degree of fire resistance and are commonly found in corridor walls and partitions between dwelling units. The critical distinction here lies in their ability to maintain continuity. If a barrier or partition is punctured by a duct or a data cable, the integrity of the entire assembly is compromised unless properly protected. We must verify that every penetration is filled with an approved fire-stopping material that meets the same hourly rating as the assembly it occupies. Smoke barriers represent a subtle but essential variation, as their primary intent is to provide a membrane capable of resisting the passage of smoke, even if their fire resistance rating is lower than that of a fire barrier. In many healthcare or high-rise occupancies, smoke is actually the primary killer, making these barriers indispensable for creating defensible spaces where occupants can be relocated. Smoke partitions, which have even lower requirements, often serve to compartmentalize corridors to keep smoke density low enough for effective egress. We rely on these membranes to create pressure differentials, working in tandem with building management systems, such as stairwell pressurization or smoke exhaust, to maintain a clear egress pathway. The design logic here is predicated on controlling the movement of buoyancy-driven gases, which tend to seek the path of least resistance through every crack or doorway. Understanding how to integrate these barriers requires a deep appreciation for the interaction between physical construction and environmental pressure. Managing vertical openings like atriums and shafts is perhaps the most challenging aspect of compartmentation, as these features naturally facilitate the stack effect and the rapid vertical spread of fire. When we design an atrium, we are essentially creating a chimney, which is why the code demands specific combinations of automatic sprinkler protection, smoke management systems, and fire-rated enclosures. Shaft protection is equally critical. Elevators, utility chases, and stair enclosures must be isolated to prevent them from becoming vertical conduits for flame and toxic gases. We calculate the allowable unprotected openings in exterior walls based on the distance between buildings, aiming to prevent the ignition of adjacent structures through radiant heat transfer. By correctly applying the geometric rules for spatial separation and parapet height, we ensure that the exterior envelope remains a reliable barrier. This is the synthesis of material science and architectural physics, aimed at containing a fire within its origin zone until it can be extinguished. I look forward to discussing how these strategies integrate into your professional practice in the next lecture. Welcome to this module on surface burning characteristics, where we will rigorously examine how materials contribute to fire growth within an enclosure. We will focus on the empirical evaluation of interior finishes and the regulatory frameworks that govern their installation. When we talk about the fire performance of interior finish materials, we are concerned with how quickly a flame front propagates across a surface. In the context of the ASTM E84 test, often referred to as the Steiner tunnel test. We measure two primary metrics to quantify this behavior. The flame spread index, or FSI, provides a numerical value comparing the material's surface burning rate to that of inorganic reinforced cement board and select grade red oak flooring. Simultaneously, the Smoke Developed Index, or SDI, assesses the relative visibility through the smoke produced during the trial. These values are not arbitrary. They reflect the thermal decomposition kinetics of the material under specific radiative and convective heat loads. By understanding the physics behind these indices, you gain the ability to predict how architectural claddings will behave during the growth phase of a fire. This information is vital for ensuring that egress pathways remain tenable for occupants during a fire event. The classification system for wall and ceiling finishes is the primary tool that codes use to regulate these materials. Class A, Class B, and Class C classifications are derived directly from the results of the Steiner tunnel test, with Class A representing the most stringent criteria. For instance, in many occupancy types, hallways and exit access corridors must feature Class A materials to prevent rapid fire spread that could cut off an egress route. These classes typically correspond to specific ranges of FSI and SDI values that architects and fire protection engineers must reference during the design phase. It is a mistake to view these as merely administrative labels. They represent thermodynamic limitations on how much energy a surface can contribute to the fire. When we analyze foam plastics, we must be even more vigilant, as their high heat release rates often necessitate specialized protective barriers. These barriers, such as thermal barriers or ignition barriers, isolate the foam from the interior atmosphere and significantly shift the ignition threshold of the assembly. Beyond the Steiner tunnel, we utilize cone calorimetry to delve deeper into the material's specific combustion properties. This test exposes a small specimen to a uniform irradiance, allowing us to calculate the heat release rate, mass loss rate, and effective heat of combustion. These parameters are essential when modeling fire spread, as they account for the transition between ignition and full room involvement. In floor coverings, the regulatory focus shifts to critical radiant flux, which measures the minimum incident radiant heat energy required to sustain flame spread. Textiles and finishings along walls and ceilings behave differently because they are subject to both concurrent and opposed flow flame spread. Concurrent flow spread, where the flame progresses in the same direction as the airflow, generally results in significantly higher propagation rates than opposed flow. Recognizing these nuances helps in selecting materials that do not exacerbate the spread of fire or introduce excessive toxic combustion byproducts into the egress path. Mastering this subject requires you to evaluate material matrices not just for their aesthetic or structural function, but for their role in the fire dynamics of the compartment. The optical density of smoke, which is related to the SDI, is a critical variable in human life safety. As smoke fills a room, it obscures exit signage and increases the likelihood of panic and displacement during evacuation. By mitigating rapid fire propagation through strict adherence to these testing standards, we control the geometry of the hazard. Remember that fire codes are built upon the assumption that the integrity of the compartment is maintained by the materials forming its interior surfaces. When those surfaces fail to meet their designated indices, the entire fire protection strategy for the building becomes compromised. Focus your study on how these indices are derived and the physical conditions they represent in the field. See you in the next lecture. Welcome to this exploration of structural fire defenses, where we will move beyond standard assemblies to analyze how building frames survive intense thermal exposure. Structural fire defense is not merely a collection of prescriptive fire-rated materials. It is an exercise in engineering a building's ability to retain its structural integrity while subjected to the thermal loads of a real, unsuppressed fire. When we discuss structural survivability, we are looking at the interaction between the fire's heat release rate, the thermal properties of the structural skeleton, and the mechanical response of load-bearing elements under high-temperature deformation. The code-prescriptive approach, relying on standardized furnace tests like ASTM E19, often serves as a baseline, but the advanced professional must grasp the thermomechanical behavior that occurs when a high occupant load or a complex layout prevents simple textbook outcomes. We must consider how, for instance, a steel beam behaves when its yield strength drops significantly at temperatures exceeding 500 degrees Celsius. and how that degradation propagates stresses to connections. If the detailing of these connections fails, the load redistribution might lead to localized damage or, in extreme cases, progressive collapse that far exceeds the initial compartment fire damage. When analyzing these buildings, we often employ performance-based structural fire engineering to move away from rigid, one-size-fits-all requirements. This requires an understanding of localized fire exposure models rather than assuming a uniform temperature distribution throughout the entire fire compartment. By utilizing computational fluid dynamics, we can predict the specific thermal profiles that will impinge upon the building frame, allowing us to estimate the actual versus the nominal fire resistance required to prevent collapse. It is crucial to remember that thermal stress does not only act through direct temperature increases in the load-bearing elements, but also through restrained thermal expansion. As structural members grow during heating, they exert massive forces onto adjacent elements, which can cause buckling or instability in secondary members that were not directly exposed to the fire. Understanding this holistic interaction ensures that our defense in depth strategy is robust enough to provide safe passage for occupants while ensuring the structure remains stable for the duration of the firefighting operations. Modern construction introduces significant challenges, particularly when we utilize engineered lumber or lightweight structural components that react to fire differently than traditional heavy steel or reinforced concrete. Engineered lumber, such as cross-laminated timber, has predictable charring rates, yet its behavior in extreme events relies heavily on the design of the adhesives and the connections used in the assembly. Lightweight construction, while efficient, often lacks the redundancy found in denser materials, making it more susceptible to abrupt, brittle failure modes under thermal stress. When an incident occurs, these materials may offer less time for emergency responders to perform their duties before the structural skeleton loses viability. We must therefore pay meticulous attention to membrane protection and the protective encapsulation of structural members, ensuring that the passive fire protection system is properly integrated into the total building design. By accounting for the specific thermophysical properties of composites and synthetic materials, we harmonize the architectural intent with the non-negotiable requirements of life safety and property preservation. Ultimately, the goal of structural fire defense is to achieve resilience by mitigating the risk of disproportionate collapse should an unexpected fire event exceed the expected fire severity. This is often achieved through a combination of inherent material performance, localized fire suppression density, and the strategic distribution of passive barriers to minimize fire spread to critical load-bearing locations. We need to evaluate whether the building can tolerate the loss of a specific support element without cascading failure, which is the cornerstone of designing for extreme event resilience. As we develop these comprehensive defenses, we must also consider the maintenance of these systems over the life of the building, as structural integrity is inextricably linked to the continued effectiveness of the fire protection measures installed. Integrating these considerations into the early design phase allows for a proactive approach that treats fire protection not as a secondary requirement, but as a fundamental aspect of the structural design process itself. This unified view ensures that even when the active systems are challenged, the physical structure performs as expected to allow for safe evacuation. I hope this overview clarifies why these architectural and mechanical considerations are so vital for the exam and for professional life. I will see you in the next recording. Welcome to the chapter on hot work permitting systems, where we will examine the rigorous regulatory frameworks designed to prevent fires during high-energy operations. This module provides the essential technical foundation required to master NFPA 51B and ensure safety in environments where welding, cutting, and grinding occur. Hot work is fundamentally an exercise in risk management where we intentionally introduce an ignition source into an environment. The NFPA 51B standard serves as our primary framework for operational control, focusing heavily on administrative structures like the permit authorizing individual, or PAI. This person holds the specific authority to verify that all safety precautions are met before work begins, effectively acting as the final checkpoint in our safety chain. Without this formal authorization, we are essentially guessing about the state of the surrounding area, which history tells us is a recipe for disaster. We must understand that a permit is not merely a bureaucratic checkbox, but a dynamic document that validates the preparation of the work environment. The PAI is responsible for ensuring that all personnel are adequately trained and that the specific hazards of the location, such as proximity to flammable vapors or dust, are explicitly addressed. By formalizing this responsibility, we shift from a culture of implicit trust to a system of verified safety. If the PAI is not properly trained to recognize the physics of thermal transfer, the entire permit system becomes an empty gesture. Therefore, our focus centers on the competence of the individual tasked with signing off on these operations. When we execute hot work, we are physically altering the environment by introducing molten metal and slag, which follow predictable but dangerous trajectories. These incandescent particles can travel surprising distances, often finding their way into floor crevices or concealed wall spaces far from the immediate point of operation. The 35-foot rule is our fundamental design benchmark here, dictating that all combustible materials must be moved at least this distance away from the hot work site. If moving the combustibles is operationally impossible, we must employ physical shielding or fire-resistant covers to prevent heat transfer. Thermal conduction through steel or concrete piping is another frequently overlooked mechanism where heat travels through structural elements to ignite material on the other side of a barrier. It is this specific failure mode that necessitates the rigorous inspection of adjacent spaces, even those not directly visible to the welder. We have to consider the conduction properties of the materials we are working near and whether those materials have the mass to act as a heat sink or the conductivity to spread the danger. Effective safety depends on recognizing that the threat extends beyond the line of sight of the operator. Monitoring the atmosphere is equally important, particularly when operating in spaces that may contain or have contained flammable gases or liquids. Operators must conduct gas testing to ensure that the environment remains below the lower explosive limit, or LEL, throughout the duration of the work. If we ignore this, we risk an explosion because the heat generated by a grinder or an oxyacetylene torch is more than sufficient to bridge the activation energy required for rapid combustion. Furthermore, the fire watch plays a life safety role that extends beyond simply having a fire extinguisher on hand and ready for use. This person must be explicitly trained to identify smoldering fires that may remain unnoticed for an extended time after the work is deemed complete. NFPA 51B recognizes that this period of observation is critical, often requiring a fire watch for at least 30 to 60 minutes after the source of ignition has been removed. By maintaining a constant presence until the area is confirmed cool, we mitigate the risk of delayed ignition that leads to structural fire loss. Treating the fire watch as a skilled observational role rather than a passive observer is a core requirement of competent facility management. Administrative controls are the glue that holds these disparate safety measures together into a coherent strategy. Auditing procedures must be in place to verify that workers are not only following the written permit, but also the spirit of the safety protocols. This involves a level of psychological awareness training where workers are coached to stop work if conditions change unexpectedly, regardless of production pressures. We are looking to eliminate the tendency to normalize risk, where recurring tasks lead to complacency and the bypassing of safety steps. An audit should not just look at whether the permit form is signed and filed away in a cabinet. Instead, a successful audit confirms that the physical reality of the job site matches the written requirements, such as verifying the fire extinguishers are functional and the shielding is intact. Integrating this level of scrutiny into daily workflows reduces the probability of human error, which remains the leading cause of industrial accidents. Mastery of this system requires us to treat every single hot work event as a high-stakes, unique operation that demands absolute focus and compliance. See you in the next lesson. Hello, welcome back. Today, we begin our deep dive into the management and storage of flammable and combustible liquids. In this chapter, we will master the technical requirements for managing flammable liquids safely, as defined by NFPA 30. This process is essential for any professional pursuing the CFPS designation because these materials represent a significant industrial hazard. We will move past simple definitions and into the thermodynamics of volatility that govern how these materials behave under pressure and temperature changes. You will learn the precise engineering standards required to build, store, and manage fuel loads in a way that minimizes risk to both life and property. This material is designed to bridge the gap between abstract physics and the practical, hard-coded requirements found in national fire codes. By the time we conclude this section, you will be proficient in evaluating containment, ventilation, and suppression strategies for high-risk solvent and hydrocarbon storage environments. Understanding the hazards associated with liquid fuel storage starts with an appreciation for the relationship between temperature and vapor production. Every flammable liquid possesses a distinct flash point, which is the lowest temperature at which it can form an ignitable mixture in air near the surface of the liquid. From an engineering standpoint, this is the fundamental threshold that determines how we categorize a material and, consequently, how we store it. We must also consider the boiling point and vapor pressure, as these variables dictate the rate at which a liquid transitions into gaseous phase, creating a potential blast atmosphere. If a substance has a high vapor pressure, it is inherently more volatile, and our storage requirements must shift accordingly to account for the increased danger of container pressurization. We often look at specific gravity as well, which tells us how a liquid will behave if a spill occurs, specifically whether it will float on water or sink and migrate through the environment. When we construct indoor liquid storage areas or dedicated warehouses, we are essentially building a reinforced environment designed to manage a latent explosion risk. The codes specify rigid structural requirements to contain fires, but perhaps the most critical engineering feature is the ventilation system. We calculate these rates based on the volume of air required to maintain the liquid's vapor concentration well below the lower explosive limit, ensuring that a leak does not immediately result in a catastrophic failure. Beyond ventilation, we must account for secondary containment, which involves calculating the spill control volume to ensure that, should a tank or barrel fail, the liquid is trapped within a controlled area rather than spreading throughout the facility. This is not just a suggestion, but a requirement for limiting the magnitude of a loss event, and the NFPA 30 standard provides the mathematical basis for sizing these containment barriers. We also emphasize explosion venting, which is designed to direct the overpressure from an internal flash fire safely away from structural members. The complexity of storing these materials extends to the fire suppression systems that we rely on when prevention fails. Standard water-based sprinklers are rarely sufficient for large quantities of flammable liquids because many of these substances are immiscible with water and would simply spread the fire if handled incorrectly. Instead, we look at specialized suppression densities that utilize foam water systems, which create a blanket that smothers the vapor production and cools the fuel surface simultaneously. We also perform a meticulous evaluation of grounding and bonding protocols for any equipment used to transfer these liquids. Static electricity is a silent and persistent ignition source. A simple spark generated by fluid friction during a transfer process can trigger a massive ignition if we have not adequately dissipated the static charge. This is why you will see specific requirements for conductive paths in piping and container management, a detail that often becomes a primary failure point during a fire investigation. Large-scale containment of massive fuel loads requires an entirely different set of engineering controls, specifically concerning tank construction and emergency relief venting. Tanks containing flammable liquids are pressurized vessels that must withstand both internal thermodynamic forces and external mechanical stresses. If a fire starts in the facility, the resulting heat will increase the pressure inside the tank, which could lead to a mechanical rupture if the vent cannot discharge the volume of vapor produced by the fire's heat flux. Emergency relief vents are sized specifically to handle this rapid rate of expansion, acting as a safeguard to prevent a boiling liquid expanding vapor explosion, or BLEV. Whether dealing with above-ground tank farms or underground storage methodologies, our goal is to maintain absolute containment through robust design and rigorous testing of all pressure-relieving hardware. These elements are the building blocks of industrial safety, and you must understand how they act in concert to contain the energy inherent in these combustible systems. See you in the next lecture. Welcome to this chapter on hazardous materials handling, where we will methodically examine the technical requirements for managing highly reactive, toxic, and unstable chemical substances. We are navigating the complex intersection of chemical stability, architectural containment, and engineered emergency mitigation strategies. In the professional practice of fire protection engineering, hazardous materials represent a distinct category of risk that transcends traditional fuel load calculations. We must begin by conceptualizing the chemical compatibility matrix, which is the foundational tool for preventing unintended exothermic reactions between disparate substances. When dealing with oxidizers, organic peroxides, or water-reactive materials, the primary objective is the segregation of chemically antagonistic species. A common failure in industrial facility design is the assumption that proximity is merely a logistical concern, rather than a critical reaction kinetics issue. Highly unstable materials, such as pyrophoric gases, demand atmospheric control through specialized inerting systems, typically utilizing nitrogen or argon blankets to eliminate oxygen exposure. We define these substances not just by their volatility, but by their reaction rates when exposed to ambient conditions or unintended mixing. The architectural response to these hazards involves strict adherence to maximum allowable quantities per control area, ensuring that if a containment breach occurs, the total energy release remains within the design capacity of the structure. When we transition to the regulatory requirements for high hazard occupancy, known as H occupancies, the level of scrutiny intensifies significantly. These facilities are designed as the final line of defense, employing sophisticated structural and mechanical enhancements to isolate hazardous events. We look at gas cabinet specifications as the first layer of hardware, which are designed to house cylinders of compressed gases and, crucially, exhaust them to a dedicated treatment system. In environments utilizing toxic gases, we mandate continuous monitoring systems that are integrated into a facility-wide emergency response network. Scrubbers are essential when the exhaust from these systems contains hazardous effluents that exceed ambient release limits allowed by environmental and fire safety codes. The synergy between these components, gas cabinets, continuous toxic gas monitoring, and scrubber systems, creates a redundant safety architecture. This system must be capable of constant operation regardless of the primary power state, necessitating robust backup power regimes for all safety-critical mechanical and sensing interfaces. The complexity of protecting modern laboratory environments or advanced manufacturing suites lies in the integration of specialized suppression systems. Unlike traditional sprinkler applications, hazardous material storage areas often require tailored suppression techniques, such as deluge systems or specialized chemical agent suppression that will not exacerbate the underlying chemical reactivity. For instance, attempting to extinguish a water-reactive fire with a standard automatic sprinkler system would be catastrophic, illustrating why we strictly forbid universal suppression strategies in these areas. Instead, we utilize fire protection methods that align with the specific hazard class, often incorporating inerting atmospheres that actively suppress the combustion environment before an ignition source can reach the activation threshold. The administrative controls, such as strict inventory management and established standard operating procedures for handling, are just as vital as the mechanical ones. Without rigorous administrative oversight, the best engineered scrubber or gas cabinet remains vulnerable to human error, which is often the precursor to significant release incidents. To master this segment of the curriculum, you must internalize the relationship between molecular stability and facility design. We are moving beyond prescriptive code adherence and into the domain of performance-based safety, where understanding the reaction kinetics of a material dictates the required spatial separation distances. If you evaluate a facility's hazardous material inventory, you are doing more than checking a list. You are quantifying the potential energy release and comparing it against the passive and active mitigation features of the building. This requires a fluency in the physical properties of cryogenics, which bring their own unique challenges regarding pressure buildup and material embrittlement. As we proceed through the assessment of these materials, maintain a focus on the continuity of containment and the fail-safe nature of the emergency mitigation devices. These systems are designed to operate under the assumption that a release event will occur, ensuring that the consequences are limited to the immediate point of origin rather than the entire facility. I look forward to seeing you in the next lecture. Hello, and welcome to this session on dust explosion prevention. We are going to explore the physics behind combustible dust hazards and the engineered safeguards required to mitigate these catastrophic risks. Combustible dust represents a unique challenge because it transforms a seemingly inert material into a potent explosive atmosphere when suspended in air. To understand this risk, we must look first at the combustible dust pentagon, which adds dust dispersion and confinement to the traditional fire tetrahedron. This model illustrates why the transition from a settled layer of dust to a suspended cloud often results in a rapid deflagration rather than a slow burn. The physics of these events are governed by parameters such as the minimum explosible concentration, which defines the lower threshold of fuel needed for ignition, and the minimum ignition energy, which quantifies the sensitivity of the dust to sparks or static discharge. These values are not theoretical estimates, but are derived from standardized ASTM testing protocols that quantify the specific chemical and physical properties of your material. When engineers design systems for facilities handling powders, they must prioritize the assessment of KST values and maximum explosion pressure, also known as Pmax. A KST value categorizes the dust into Saint classes, which dictate the necessary intensity of downstream protection like venting or suppression. If you are designing pneumatic conveying systems, you are essentially creating a potential conduit for flame propagation if the dust velocity and concentration are not strictly managed. Dust collection topologies, particularly baghouses, function as concentrated reservoirs for hazardous concentrations of fuel, and the fluid dynamics within these units must be balanced to prevent stagnant zones where material can accumulate. A failure to recognize the pressure carrying capacity of these ducts often leads to structural failure during an internal event. Housekeeping is often dismissed as a purely administrative task, but in the context of explosion prevention, it is a critical life safety function. The primary danger in large industrial facilities is not necessarily the initial primary explosion, which may be localized within a piece of equipment, but the subsequent secondary explosion caused by the shock wave dislodging overhead dust. This leads to a domino effect where previously dormant, settled dust is lofted into the air, creating a massive facility-wide fuel source for a much larger blast. Consequently, facility managers must implement rigorous, documented housekeeping protocols that ensure dust accumulation never reaches the thickness levels that could fuel a secondary event. This is why vacuum cleaners used in these environments must be intrinsically safe and rated for hazardous locations, as a standard vacuum could serve as an ignition source itself. Engineers address these risks by deploying a layered defense strategy, starting with explosion venting to manage the rate of pressure rise. Venting panels are designed to relieve internal pressures before they reach the structural limits of the vessel, but they must be located so that the discharged flame ball does not endanger personnel or adjacent infrastructure. In scenarios where venting is impossible, such as inside indoor silos, we turn to chemical suppression systems that detect the onset of a pressure rise via high-speed sensors and flood the volume with an extinguishing agent in milliseconds. Isolation valves are equally essential, as they create a physical barrier to block the propagation of the flame front from the machine to the rest of the facility. These systems rely on spark detection arrays that can identify an ignition source long before a dust cloud ignites, providing an automated window for shutdown protocols. The electrical configuration of these facilities requires strict adherence to hazardous area classifications to ensure that no equipment serves as an ignition source for the surrounding dust. This involves using dust ignition-proof enclosures and avoiding dust-tight installations that fail to account for the unique thermal conductivities of the material being processed. Every motor, light fixture, and control panel must be selected based on the specific classification of the hazardous zone. This systematic application of engineering controls, combined with operational discipline, is the only way to manage the volatility of an industrial environment where combustible materials are handled at scale. Understanding these interactions is vital for any professional involved in the fire protection of industrial and agricultural storage facilities. I will see you in the next lecture. Hello. Today we are diving into the complex domain of industrial fire hazards, where the stakes are elevated by the scale and nature of processing operations. In heavy industrial and manufacturing environments, fire protection engineering shifts from standard prescriptive requirements toward a rigorous performance-based analysis of specific process risks. We must understand that industrial ovens and furnaces are not merely heating vessels, but potential bomb sites if solvent vapor accumulates beyond their design thresholds. Monitoring the lower flammability limit, or LEL, is critical, as any deviation toward the stoichiometric mixture within the oven creates an immediate explosion hazard upon ignition. Ventilation becomes your primary line of defense, requiring precise exhaust rates to maintain vapor concentrations well below the LEL, typically verified by interlock sensors that shut down the heat source if airflows fall below set points. When internal fires do occur due to flash-off from coatings, These enclosures often necessitate high-speed deluge systems to suppress the fire before structural integrity is compromised. You should view these systems not as general suppression, but as specialized containment strategies integrated directly into the process control logic of the manufacturing line. Moving into specialized areas like semiconductor fabrication, the risk profile changes entirely to address high-value cleanroom environments and the storage of process-specific hazardous gases. These facilities require extensive gas monitoring and secondary containment for piping systems to mitigate the release of toxic or pyrophoric materials. Similarly, industrial dipping and coating processes present a distinct peril due to the presence of flammable vapors evolving from large open vats or drying tunnels. These operations require meticulous control over liquid levels, drag-out collection, and electrical classification of the surrounding room to prevent ignition of the vapor-air mixture. In aerosol filling facilities, the density of energy is much higher, and the design must account for the rapid release and combustion of propellants. Each of these unique occupancies demonstrates that a one-size-fits-all approach to fire protection is insufficient. Engineering judgment must always be tempered by the specific chemical and physical characteristics of the materials in motion within the facility. The emergence of lithium-ion battery energy storage systems, commonly referred to as ESS, introduces a unique and particularly volatile risk known as thermal runaway. This phenomenon occurs when a cell's internal temperature rises uncontrollably, leading to the venting of flammable, toxic gases and the eventual cascading ignition of adjacent cells. Unlike a simple hydrocarbon fire, thermal runaway creates its own oxygen source and produces significant quantities of hydrogen and carbon monoxide, which can lead to explosive atmospheres even in large, well-ventilated rooms. Protection strategies must evolve beyond standard sprinklers to include early warning gas detection and, potentially, water curtain separation or inert gas suppression to limit the propagation of the event. As fire protection specialists, we must evaluate the battery chemistry, the state of charge management, and the physical spacing between modules to determine the adequacy of existing protection. This is a rapidly advancing field where the rate of technological change often outpaces the development of consensus standards, requiring you to rely on fundamental principles of thermodynamics and chemical reactivity. Finally, we must consider the mechanical processing of heavy timber and similar combustible commodities, where the risk is predominantly related to bulk storage and the potential for deep-seated fire development. While these are not chemical-heavy industries, the massive fuel loads and the potential for obstructed fire growth require advanced compartmentation strategies and structural resistance considerations. When evaluating these facilities, your focus should remain on the interface between the ignition source, be it mechanical friction, electrical failure, or human error, and the vast fuel load available. It is our responsibility to ensure that the suppression systems, whether they are automatic sprinklers or manual hose streams, are capable of reaching the seat of what could become a significant structural event. By integrating the knowledge of these varied industrial hazards, you develop the comprehensive expertise required to safeguard complex manufacturing and energy production environments. I look forward to discussing the next section with you. Welcome back. We are moving into the domain of logistics and storage facilities where the fire risk profiles are significantly elevated due to fuel load density. In this chapter, we will master the engineering principles required to protect massive volume warehouses and complex racking environments. Modern logistics centers present a unique challenge because the sheer volume of fuel gathered in high-piled configurations defies traditional suppression logic. When we analyze these environments, our primary concern is the classification of commodities, which dictates the fundamental heat release rate we must design against. We are categorizing products based on their combustibility and arrangement, specifically focusing on how encapsulated plastics or the accumulation of idle pallets radically alter fire growth curves. A plastic product does not burn like a piece of timber. It releases energy at a significantly higher rate, often necessitating a more aggressive suppression response. By understanding these commodity classes, you gain the ability to predict the fire dynamics before they begin, which is the cornerstone of professional fire protection engineering. If you fail to account for the correct commodity class, your hydraulic calculations for suppression systems will inevitably fall short of providing the necessary density to control a fire. Once we determine the fuel characteristics, we must turn our attention to the physical geometry of the storage arrays themselves. The movement of fire plumes through vertical and horizontal flue spaces is a complex fluid dynamics problem that often baffles those unfamiliar with rack storage. In double row or multiple row rack configurations, these flue spaces act as chimneys, accelerating the vertical spread of heat and smoke. If a fire starts at the lower levels of a high-piled rack, it is immediately funneled upward, bypassing the ceiling-level sprinkler activation threshold unless we design the path correctly. We must also consider how solid shelving interferes with the cooling effect of water droplets, effectively shielding the fire from the sprinklers. Designing for these environments requires more than just following a table in a code book. It requires a deep understanding of how fire plumes interact with physical barriers within the rack structure. Suppression in these environments usually relies on either early suppression fast response, known as ESFR, or control mode specific application, or CMSA sprinklers. The hydraulic demand for these systems is hyper-specific because they are designed to perform a distinct task. An ESFR system aims for true suppression, meaning it must discharge water at a high enough density and velocity to reach the base of the fire and interrupt the combustion process during the early stages of growth. Conversely, CMSA systems are primarily designed to control the fire, essentially soaking the surrounding fuel to prevent horizontal fire spread until the fire department arrives. Choosing the wrong technology for the specific racking geometry can lead to cascading system failure, where the heat output overwhelms the water discharge capacity. You must ensure that the piping network and the available water supply are sufficient to meet the specific discharge requirements for the chosen technology at the most remote area of the rack. Beyond the sprinklers themselves, we have to consider the environment's interaction with smoke and heat venting systems. A common failure mode in modern warehousing is the phenomenon of sprinkler skipping, which occurs when draft curtains or poorly placed vents redirect smoke away from sprinkler heads, delaying their activation. When sprinklers activate too late, the fire may have already reached a point where the local water density is insufficient for suppression. Facility management plays a critical role here because even the best engineering design can be rendered useless by poor housekeeping. If aisle widths are compromised or storage height limits are exceeded, you have essentially changed the variables of the original fire model. Rigid facility management is not just a policy preference for the owner. It is an absolute necessity for the integrity of the fire protection system that you have designed. See you in the next lecture. Welcome back. Today, we begin our module on loss prevention, where we will synthesize organizational risk management with physical fire protection engineering. Loss prevention is often mistaken for merely installing a sprinkler system, but from an enterprise perspective, it is a deliberate integration of property conservation and business continuity planning. When we manage risk, we are not simply checking boxes for code compliance. We are establishing a comprehensive defensive posture that accounts for the entire life cycle of an asset. We begin by identifying vulnerabilities through a systematic evaluation of physical infrastructure and operational workflows. Once these vulnerabilities are mapped, we must establish quantitative risk tolerance thresholds that align with the organization's financial appetite. These thresholds serve as the foundation for a defense in-depth approach, which layers administrative controls, like training and hot work permits, over physical hardware such as specialized suppression systems. Without this holistic strategy, even the most robust fire protection system can be rendered ineffective by a failure in organizational process. To make defensible decisions, we must engage with the financial mathematics of risk, specifically the distinction between maximum foreseeable loss and normal foreseeable loss. Maximum foreseeable loss represents the worst-case scenario, assuming that all primary fixed suppression systems fail and fire department intervention is delayed, whereas normal foreseeable loss focuses on the impact of typical operational hazards and minor incidents. When an organization considers the capital expenditure for advanced fire protection, they are weighing the cost of hardware against the potential for cascading operational downtime. This is where cost-benefit analysis becomes critical for the fire protection specialist. You are essentially acting as a bridge between the engineering department and the executive suite, translating technical reliability into monetary value. If the annualized cost of a failure exceeds the amortized cost of the protection system, the business case for installation becomes clear for stakeholders. Maintaining this safety posture requires meticulous attention to the human element. which often proves to be the weakest link in any loss prevention program. A robust impairment management scheme is non-negotiable. You must have formal procedures governing the temporary shutdown of protection systems during maintenance or impairment events. If a sprinkler valve is closed for repairs, an auxiliary strategy, such as a fire watch or pre-planned temporary protection, must be triggered immediately. Furthermore, emergency response organization training must be integrated into the broader corporate culture to ensure that personnel are not merely bystanders, but active participants in the preservation of the facility. This involves regular tabletop exercises that simulate the loss of primary critical infrastructure and test the resilience of communication protocols across departments. Predictive maintenance scheduling for fire pumps, detectors, and control panels must be treated with the same urgency as production machinery maintenance. Ultimately, establishing a resilient corporate safety culture requires you to synthesize disparate sources of data, ranging from raw actuarial statistics to complex engineering economics. You are not only designing systems to suppress fires, but you are also building institutional memory that guards against the complacency that often creeps into stable environments. Communication remains the final pillar of this strategy, as technical findings must be articulated in terms of strategic business continuity to resonate with executive leadership. When you can explain how a fire-resistant design choice preserves market share or prevents a debilitating interruption in logistics, you move from being a cost center to a vital partner in enterprise stability. Mastery in this field demands both an analytical mind for risk assessment and the diplomatic skill to champion these methodologies across the entire organization. See you in the next lecture. Welcome to our discussion on fire investigation principles, where we will translate scientific rigor into the fundamental task of determining the origin and cause of fire events. In this chapter, we will master the systematic methodology mandated by NFPA 921 for post-fire forensics, ensuring your investigative conclusions remain intellectually defensible and resistant to scrutiny. By the time you complete these lessons, you will possess a structured framework for evidence collection, hypothesis generation, and the elimination of alternative causes that is essential for every certified protection specialist. Effective fire investigation requires a strict adherence to the scientific method, as a forensic analysis is only as reliable as the logical framework supporting it. We begin by defining the problem, which often involves an initial assessment of the scene to establish the scope of the investigation. Once the incident is defined, we move to data collection, which encompasses everything from physical evidence to witness statements. The critical step involves the formation of a hypothesis that must be tested against the empirical data gathered at the scene. If the data contradicts the hypothesis, we must discard or refine our theory, as the investigation must be driven by objective evidence rather than preconceived notions. This iterative process prevents cognitive biases like confirmation bias, which can lead even experienced investigators to settle on an incorrect origin or cause prematurely. Tracing fire propagation requires an understanding of how smoke and heat movement manifest as physical indicators on structural elements. We look for thermal degradation, such as the spalling of concrete where the rapid expansion of trapped moisture causes the surface to pop off under high heat. Calcination of gypsum board, characterized by the loss of chemically bound water, provides another proxy for duration and intensity of exposure when properly measured. By mapping these patterns, you are performing a vector analysis that allows you to trace the fire back to its incipient source. You must remain aware that fire behavior in an enclosure is influenced by ventilation and structural geometry, which may create misleading patterns that do not necessarily point toward the area of origin. Consistent application of these dynamics allows us to reconstruct the fire's history with higher geometric and temporal precision. The identification of an ignition source demands a methodical, exhaustive approach to eliminate all potential accidental or natural causes. When we examine electrical arc mapping, we look for physical evidence of localized heating on conductors, which helps differentiate between arcing as a cause of the fire versus arcing as a consequence of fire heating. Appliance failure analysis involves examining internal components to determine if a mechanical or electrical failure occurred within the device or if it was merely consumed by external fire growth. Accelerant detection, whether through chemical sampling or the use of canine teams, must be handled with extreme care to maintain the chain of custody. Any piece of physical evidence collected must be documented, labeled, and secured in a manner that precludes tampering or contamination, as this is the bedrock of any legal or administrative forensic procedure. Human testimony often provides the contextual layer that physical evidence lacks, yet it must be weighed carefully against the hard data found at the scene. Interviewing witnesses requires a technical approach designed to elicit accurate descriptions of the fire's initial state without inadvertently planting suggestions. We must compare witness reports of the fire's growth with the thermal signature left behind by the actual combustion. If a witness reports a fire starting in an area that shows only light smoke damage and no heat-related destruction, that testimony must be evaluated as a potential inconsistency. Developing these interviewing skills allows the investigator to bridge the gap between people and physics, ensuring that narrative accounts do not conflict with the immutable laws of thermodynamics. Computational fire modeling has become an indispensable tool for validating the chronological development of a fire hypothesis. You can use software to input structural dimensions, fuel loads, and environmental conditions to simulate how the fire should have progressed under specific parameters. If the simulation results align with the physical patterns documented during the scene investigation, the confidence in your hypothesis grows significantly. Of course, the model is only a reflection of the data provided to it, meaning your initial field measurements must be accurate for the output to have any forensic utility. By integrating these digital tools with traditional field analysis, you create a robust, multi-layered report that stands up to the rigors of any insurance inquiry or legal proceeding. See you in the next lecture. Hello, and welcome to this deep dive into risk assessment methodologies for fire protection engineering. In this module, we will explore the mathematical and logical frameworks used to quantify fire risk in complex environments, ensuring you gain the expertise required to pass the CFPS exam with confidence. You will learn how to transition from basic code compliance to advanced probabilistic modeling, allowing you to justify engineering decisions through data-driven analysis. Mastering these quantitative tools is what distinguishes a competent professional from a true specialist capable of handling high-stakes structural fire design. We will dissect the most rigorous methodologies, providing you with a roadmap to successfully navigate the analytical challenges presented in the certification process. When we talk about risk assessment in modern fire protection, we are moving away from purely prescriptive compliance and toward performance-based engineering. The transition requires a shift in how we view the reliability of fire protection systems and occupant behavior. Fault tree analysis, or FTA, serves as our primary deductive tool here. It allows us to visualize how various independent component failures can cascade into a catastrophic top event, such as a full-scale fire spread. By breaking down the system into a Boolean structure, we identify the minimal cut sets that represent the most significant vulnerabilities in our architectural or mechanical designs. This approach forces us to treat every suppression component not as a black box, but as a probability function with a measurable rate of failure. If FTA is our deductive tool, event tree analysis, or ETA, is our inductive partner designed to model the progression of a fire once ignition has occurred. We start with an initiating event and follow the branching logic of system interventions, such as detection, suppression, or compartmentation activation. This logic reveals the conditional probabilities inherent in a fire event, allowing us to quantify the likelihood of success or failure at every stage of the incident timeline. When these trees become overly complicated, we often turn to Monte Carlo simulations to iterate through thousands of potential fire scenarios. By randomly sampling from the probability distributions of variables like heat release rates or ventilation availability, we produce a distribution of possible outcomes rather than a single, unreliable deterministic point estimate. Failure mode and effects analysis, or FMEA, rounds out our analytical toolkit by focusing on the component level of hardware systems. Unlike FTA, which starts with a major failure, FMEA begins at the lowest level of an assembly to determine how a specific mechanical fault impacts the overall system integrity. In the context of nuclear facilities or complex transportation hubs, this is non-negotiable, as even a small relay failure could lead to an undetected fire. We must categorize these failures by their severity and their likelihood of occurrence, effectively creating a risk priority number. The integration of these varied data streams into a single risk matrix allows us to prioritize capital expenditures for fire suppression upgrades in a way that respects budget constraints while maximizing life safety. Applying these methods to historical heritage structures or delicate infrastructure requires a nuanced understanding of human response probabilities. We calculate the time required for detection, the delay in occupant reaction, and the actual egress speed, often using stochastic models to account for the heterogeneous nature of building users. It is an exercise in synthesizing abstract statistical probabilities into actionable safety parameters that local authorities can verify and accept. You are effectively building an argument that a specific design, perhaps a non-standard suppression layout or an unconventional egress route, provides an equivalent level of safety to a prescriptive code solution. This synthesis of logical deduction and mathematical proficiency is exactly what the CFPS exam expects you to demonstrate when evaluating real-world hazard scenarios. I will see you in the next lecture. Welcome to the module on Building Code Application. In these lessons, we will dissect the legal and engineering frameworks that govern modern fire protection and safety requirements. Understanding building codes requires moving beyond a simple checklist approach to embrace the hierarchy of regulatory architectures. At the core of this discipline lies the distinction between the International Building Code and NFPA 5000, both of which serve as foundational models that jurisdictions adopt, amend, and enforce as law. When we look at these documents, we must recognize that they do not exist in a vacuum, but rather interact with a complex, overlapping web of local ordinances and state-level mandates. For any given project, the engineer must identify which code is legally binding, which requires a rigorous assessment of jurisdictional adoption cycles and local amendments. This task is rarely straightforward because municipalities often layer their own specific requirements for structural fire resistance or site access on top of the base standards. You are effectively navigating a multi-layered legal environment where the engineering solution must satisfy the most restrictive applicable requirements. If you misidentify the governing code, the entire design process, no matter how technically sound, becomes legally invalid and functionally useless. Mastering this hierarchy is the barrier to entry for professional practice, as it represents the fundamental framework upon which every fire protection system is built. Once the legal framework is established, the application of code requirements turns to the physical configuration of the building, specifically through occupancy classifications and construction type analysis. Occupancy is the primary driver for almost every subsequent design decision, as it dictates the levels of hazard the code assumes for the building's inhabitants. For instance, an institutional occupancy, such as a hospital, mandates significantly more stringent requirements for egress and compartmentation than a low-hazard storage facility. When we marry these classifications with construction types, we define the inherent fire resistance of the structure and the allowable limits on building height and area. These limits determine whether a project is viable under prescriptive requirements or whether the design team must look for alternatives. The code presents these variables as a matrix where the size of the building is intrinsically linked to the fire protection features you provide. If you choose to increase floor area beyond prescriptive limits, the building code typically requires the installation of automatic suppression, creating a classic trade-off between passive and active protection. This dynamic illustrates how fire protection is not merely an add-on, but a feature defined by how the building is classified and constructed from the start. Beyond the prescriptive paths, we must address the administrative mechanisms that allow for innovation through performance-based design and variance requests. When a design falls outside the strict parameters of the code, registered design professionals often utilize the alternate materials and methods clause to justify their approach. This process is not a loophole, but an engineering-driven justification that requires a high degree of technical rigor and documentation. You must prove to the authority having jurisdiction that the proposed alternative achieves an equivalent level of safety to the prescriptive code requirement. This often involves fire modeling or quantitative risk assessment to demonstrate that the outcomes meet or exceed the performance objectives of the governing regulations. However, with this flexibility comes the professional burden of documenting every assumption and calculation with absolute clarity. The authority having jurisdiction expects transparency because they are ultimately responsible for the safety of the public in their jurisdiction. If your documentation is ambiguous, you face a significant risk of project delay or total rejection during the review stage. Consistency and compliance documentation acts as the connective tissue between design intent and the eventual certificate of occupancy. Throughout the life cycle of the building, every change, substitution, or field adjustment must be mapped back to the original code requirements to ensure the regulatory chain of custody remains unbroken. This is especially true when dealing with the appeals process, where technical disagreements between the designer and the reviewer must be adjudicated formally. To succeed in this area, you must approach code application as a technical audit of the building's life safety strategy. Every decision regarding fire-rated assemblies, means of egress widths, or suppression system performance must be defensible against both engineering scrutiny and legal audit. By maintaining meticulous records, you not only ensure compliance, but also provide the necessary clarity for facility managers who will take over the building after you have finished your work. Fire protection is an ongoing responsibility that starts at the conceptual design phase and concludes only when the building is decommissioned. See you in the next lecture. Welcome to the module on plan review processes, where we will examine the systematic engineering oversight required to ensure building designs comply with safety standards. In this chapter, we will dissect the rigorous methodology involved in verifying that architectural and engineering plans align with life safety and fire protection requirements before construction commences. We will explore the critical audit trails required for evaluating floor plans, egress geometries, and structural fire resistance details. You will learn how to systematically cross-reference sprinkler shop drawings and fire alarm system layouts against established codes. Understanding this process is essential for any professional aiming to pass the CFPS exam, as it bridges the gap between theoretical code application and practical facility implementation. By the end of this module, you'll be equipped to identify potential design conflicts, such as those between HVAC ductwork and sprinkler routing, which are common points of failure in complex infrastructure projects. The plan review process is fundamentally an exercise in risk mitigation through documentation analysis and verification of compliance. When we approach an architectural set, we begin by verifying the intent of the space against the occupancy classification, as this dictates the entirety of the subsequent life safety engineering. We must scrutinize egress geometries to ensure the calculated travel distances and clear widths are not compromised by the placement of fixed furniture or architectural features. This requires a careful examination of floor plans where we check for the continuity of fire-rated barriers, ensuring that vertical and horizontal penetrations are addressed through adequate fire-stopping details. It is not sufficient to simply observe a wall on a plan. We must verify the fire resistance rating of the assembly against its intended function, such as protecting a stairwell or a hazardous storage area. Moving into fire alarm and sprinkler shop drawings, the verification shifts toward technical capacity and hardware compatibility. For sprinkler systems, we review hydraulic calculations by validating that the provided supply curves are not only accurate, but represent the worst-case water demand scenarios for the building. This involves checking pipe schedule cross-references against the calculated nodal pressures to ensure the friction losses were accounted for correctly in the design. Simultaneously, we inspect the equipment cut sheets to confirm that every device, from sprinkler heads to smoke detectors, holds the correct listing and approval for its specific environment. When we audit electrical pathways, such as notification appliance circuits, we look for voltage drop confirmations to guarantee that the system will function under battery backup during a power loss. Multidisciplinary coordination is perhaps the most challenging aspect of this review because it requires the engineer to overlay conflicting systems to find hidden hazards. A common scenario is the installation of large HVAC supply ducts that obstruct the discharge pattern of a ceiling-mounted sprinkler head, violating the spray coverage requirements. We must also scan for fire-rated barriers that have been breached by electrical cable trays or plumbing runs without the appropriate listed through penetration protection. Identifying these conflicts before they become field issues prevents costly rework and, more importantly, ensures the fire protection strategy remains cohesive. We must treat every plan as a dynamic system where a change in ventilation can influence smoke control and, by extension, the egress time calculations we previously audited. Ultimately, this discipline demands an intense focus on microscopic details, where even a slight error in a pipe sizing calculation or a missing door label can jeopardize the entire safety profile of a building. We must maintain a skeptical perspective, asking ourselves how each component interacts with the fire protection system as a whole if an incident were to occur. This is not about trusting the designer's intent, but about verifying the reality of the engineering presented on the page against the rigors of the NFPA standards. By adopting this methodical, evidence-based approach, you will refine your ability to preemptively identify design flaws that lead to catastrophic failures. Continue your study of these processes to build the technical intuition necessary to audit any facility design with confidence. See you in the next lecture. Welcome back to our journey towards CFPS certification, where we now shift our focus toward the intersection of engineering and financial security. This chapter addresses insurance risk mitigation, specifically focusing on how property insurance engineering and highly protected risk standards influence corporate law strategy. In the professional landscape, we occasionally encounter the assumption that meeting the minimum requirements of a municipal building code is sufficient for business operations. While code compliance is legally mandatory, it often represents the minimum threshold of safety, which may not align with the risk appetite of an insurance underwriter or a global corporation. Highly protected risk, or HPR programs, represent a class of insurance underwriting that necessitates engineering standards significantly more stringent than those mandated by local jurisdictions. When an insurance carrier designates a property as an HPR facility, they are effectively stating that the risk is mitigated to a degree where a total loss is highly improbable. This requires you to look beyond the prescriptive requirements of the NFPA standards and understand the probabilistic nature of modern property insurance engineering. One of the primary drivers of these programs is the independent engineering survey conducted by insurers like FM Global, which evaluates a facility across several distinct dimensions. These surveys are not focused solely on fixed fire protection systems, but rather on the combination of physical hazards, human element programs, and natural catastrophe exposures. The human element is often the most critical factor in these evaluations because mechanical systems are useless if they are impaired or disabled. Underwriters scrutinize policies involving hot work permits, fire protection system impairment procedures, and routine maintenance schedules to confirm that the organization is actively managing its risk. If the human element program is flawed, the most expensive automatic sprinkler system in the world may fail to prevent a catastrophic loss. From a financial perspective, you must understand how these physical protections translate into actuarial value and premium optimization. An insurance premium is essentially the cost of transferring risk, and underwriters utilize complex models to determine the probability of a fire event and the expected loss magnitude. When a company invests in advanced fire protection, such as early suppression fast response sprinklers or automated smoke control systems, they are not just performing a safety function. They are actively lowering the enterprise's loss expectancy, which allows for the negotiation of lower premiums or higher deductibles. This, in turn, protects the company's balance sheet and ensures better liquidity in the event of an otherwise devastating business interruption. Business interruption is arguably the most significant financial concern for modern industrial organizations, often far exceeding the physical damage to assets. A minor fire in a critical manufacturing facility can halt an entire supply chain, leading to contractual penalties and loss of market share. Your task is to calculate the business interruption values by assessing the downtime required to replace specific hardware or critical raw materials. By implementing strategic fire protection enhancements, you essentially build a form of self-insurance against these operational failures. We are aiming for a scenario where the cost of engineering controls is lower than the lifecycle cost of high-risk insurance premiums and potential operational downtime. Finally, we must account for natural catastrophe exposures, which are increasingly managed through the same rigorous engineering assessment frameworks. Flood, seismic activity, and windstorm events require physical building modifications that go beyond fire-centric design, such as elevation changes or reinforced structural integrity. Risk transfer mechanisms are deployed when the residual risk, what remains after all engineering controls have been applied, is still too high for the corporation to carry alone. You need to view fire protection engineering as a subset of corporate finance, where every sprinkler head and fire-rated partition contributes to an optimized risk profile. Bringing these disciplines together is how a certified fire protection specialist provides measurable value to their organization. We will continue our exploration in the following segment. Welcome back to the final module of our curriculum. In this concluding session, we will synthesize the 7 domains of fire protection engineering into a unified framework for professional practice. Congratulations on reaching the culminating phase of this certification preparation journey. Over the course of our previous modules, we have dissected fire dynamics, life safety architectures, suppression systems, and complex risk management methodologies. You have wrestled with the physics of combustion, the nuances of hydraulic calculations, and the rigorous requirements of global life safety standards. This final review is designed to consolidate that knowledge, ensuring that you view these disparate topics not as isolated facts to be memorized, but as a cohesive, holistic system of protection. By integrating active suppression with passive containment and human operational protocols, you develop the versatility required to address the multi-dimensional challenges found in modern fire protection engineering. This mastery of technical vocabulary and scientific principles is precisely what distinguishes a certified professional from a general practitioner, providing you with the necessary tools to safeguard life and property in an increasingly complex industrial world. As you prepare for the examination, it is important to reflect on the interplay between the different domains we have covered. A robust fire protection strategy relies on the fact that no single system can function in a vacuum. Rather, each component depends on the integrity of the others. For example, the effectiveness of an automated suppression system is inextricably linked to the early notification provided by a detection network, while both are limited by the building's passive compartmentation and structural fire resistance. We have seen how enclosure fire behavior affects the thermal load on a structure, which in turn dictates the demand placed on the water supply and pump systems. By holding all these variables in your mental model simultaneously, you avoid the common pitfall of hyper-focusing on one component while neglecting the cascading effects of a failure elsewhere. This synthetic approach is the hallmark of effective fire safety engineering and will serve as your primary strategy for navigating the complexity of the certification exam. We must also refine our approach to the testing environment by focusing on the application of formulas and the interpretation of high-level requirements. You have practiced these calculations during our deep dives into hydraulics, pump sizing, and occupant load determination. But now, you must focus on speed and accuracy. Remember that the examination often tests your ability to select the correct standard or methodology before you even begin the calculation. So prioritize your analytical process. When you encounter a multi-domain scenario on the exam, begin by identifying the occupancy classification and the primary hazard, as these factors typically dictate the constraints for both egress and suppression. If you find yourself stuck, return to the core principles of fire dynamics or life safety that we discussed at the start of this course. These fundamental truths remain the bedrock upon which all technical codes are written and are the key to unlocking difficult questions. Your readiness to achieve certification is not merely a product of the hours spent reviewing technical data, but of your capacity to think critically about fire safety as a whole. You are now equipped to manage industrial fire hazards, oversee complex facility logistics, and apply risk-based strategies to mitigate potential losses. This professional capability allows you to transition from theoretical understanding to immediate, impactful application in the field. As you step forward to sit for this exam and ultimately apply your expertise, remember that the standards we have studied exist to provide a measurable, repeatable safety baseline. By adhering to these benchmarks while maintaining a deep understanding of the underlying science, you become an essential asset to your organization and the broader life safety community. Your commitment to this discipline mirrors the rigor of the profession itself, and I am confident that you are prepared to demonstrate that proficiency. I wish you the very best of success as you take this final step in your certification journey. See you in the exam center.